Imagine walking down to a beach you've known your entire life. The same rocks, the same tide pools, the same horizon you've watched 1,000 sunsets sink into. Now imagine coming back a few years later, and that beach is just gone. Not eroded slowly, not nibbled away over decades. Gone, swallowed. The horizon itself has moved, and the place where your grandparents fished, where your community built its homes, where generations of footprints once pressed into the sand, is now 50 feet underwater. That's not science fiction. That's a real possibility scientists are investigating for a moment in history so strange, so poorly understood, that we're still arguing about what actually happened. Around 10,300 BC, something occurred to global sea levels that shouldn't have been possible. Water that had been locked away as ice for tens of thousands of years suddenly began pouring into the oceans at a rate that defies easy explanation. And the question we're chasing today is simple to ask, but brutally hard to answer. How fast did this actually happen? Fast enough for a single generation to watch their coastline disappear? Fast enough that communities didn't have time to pack up and move inland? Fast enough that entire settlements, whatever they may have looked like, were left behind, drowned and forgotten? Let's be clear about something right away, because this is where a lot of popular retellings go wrong. Nobody is claiming that oceans rose overnight in a single catastrophic night, like some biblical flood arriving with a thunderclap. That's not what the evidence shows, and we need to be honest about that distinction from the very beginning. What the evidence does show is something almost as unsettling. A period of extraordinarily rapid change compressed into what geologists call a meltwater pulse, happening at the tail end of the last ice age, when the planet was undergoing one of the most dramatic environmental transformations in its entire history. Whether that transformation happened over a single lifetime, a few generations, or a couple of centuries is exactly the mystery we're going to unpack. And this investigation takes us everywhere. We're going to look at the ice sheets that held back unimaginable volumes of water, and what happened when that water finally broke free. We're going to explore submerged landscapes, places like Doggerland in the North Sea and the drowned lowlands of Sundaland in Southeast Asia, regions where people almost certainly lived before the water took everything. We're going to ask what archaeology can and can't tell us about lost settlements sitting under meters of sediment and ocean. We're going to dig into flood myths and oral traditions passed down for thousands of years, and ask whether some of them might be distant, garbled memories of watching the world's coastlines rearrange themselves. And we're going to sit with the scientific disputes too, because this is not a settled topic. Researchers disagree, sometimes sharply, about timing, about causes, about how dramatic the human impact really was. Before we go further, I want to know where you're listening from and what time it is right there. I read these comments constantly, and it's honestly one of my favourite parts of doing this. Someone's listening in Manila before sunrise, someone else is falling asleep in Toronto at midnight, and somehow we're all here together, untangling the same 12,000-year-old mystery. Drop it below. And if you want to actually support what we're building here, the single best thing you can do is follow the show on Spotify and leave a 5-star review. It costs nothing. It takes 30 seconds, and it genuinely helps more people discover these stories. The link is right there in the description. Now, let's start where all good mysteries start. With ice. So let's start with the date itself, because 10,300 BC sounds impressively precise. Like someone was standing there with a calendar watching the tide creep up, marking the day on a wall. That's not how this works, and understanding why is actually the first step to understanding the whole mystery. When scientists say something happened around 10,300 BC, they're not reading off a wristwatch. They're translating between several different systems of time, and each translation introduces a little fuzziness. Here's the problem in plain terms. Most of what we know about ancient sea levels and ice sheets comes from radiocarbon dating. You take a sample, maybe a piece of ancient wood, a bit of peat, a fragment of shell pulled from a drowned shoreline, and you measure how much of its radioactive carbon has decayed. That gives you what's called a radiocarbon date, or a radiocarbon year. Here's the catch. Radiocarbon years are not the same length as calendar years. The amount of carbon-14 in Earth's atmosphere hasn't stayed perfectly constant over the last 12,000 years. It's wobbled because of changes in cosmic ray activity, shifts in the carbon cycle, even the Earth's magnetic field doing its own slow drift. So a raw radiocarbon date can actually be off from a real calendar date by centuries. To fix this, scientists use something called calibration. They compare radiocarbon measurements against other records where we know the actual calendar age already. Things like tree rings that can be counted year by year, or layered lake sediments, or ice cores with visible annual bands. This process converts a raw radiocarbon year into what's called a calibrated year before present, usually written as Cal-BP. So when you see a date for this period, it might show up as a radiocarbon year, a calibrated year before present, or converted all the way into a BC or BCE calendar date. And depending on which system a particular research paper is using and which calibration curve they applied, and how old that calibration curve was when they published, you can end up with dates for the same event that differ by a few hundred years between two different studies. That's not sloppiness, that's just the nature of trying to pin an exact number on something that happened over 10,000 years ago, using tools that have themselves been refined and re-refined for decades. This is actually really important to sit with for a second, because it explains something that trips up a lot of people when they start reading about the end of the Ice Age. You'll see one book say an event happened 11,500 years ago. Another source says 12,700 years ago. A documentary says 10,300 BC. A scientific paper says 8,300 BC. These aren't necessarily contradicting each other. They might be using different dating conventions, different calibration models, or referring to slightly different phases of a process that didn't happen in one clean moment anyway. Keep that in your back pocket, because we're going to run into it again and again as we dig through the evidence. So where does 10,300 BC actually sit in the bigger picture? Roughly speaking, this date lands right around the boundary between the end of the last ice age and the beginning of what we now call the Holocene, the geological epoch we're still living in today. Think of it as the hinge point. Before this window, the planet is still deep in the grip of glacial conditions, ice sheets, kilometres thick, sitting over huge portions of North America and Northern Europe. After this window, the world starts looking recognisably modern. Forests spreading, temperatures stabilising, the climate settling into the relatively calm and predictable pattern that would eventually make agriculture, cities, and civilization possible. But that transition wasn't smooth. It was messy, chaotic, full of fits and starts, sudden warm snaps followed by shocking cold reversals. And it's inside this turbulent stretch of time, this hinge between Ice Age and Holocene, that the meltwater pulse we're investigating appears to have occurred. Now here's where we need to slow down and be really careful, because this is exactly the kind of thing that gets flattened and oversimplified in popular retellings. There is not universal agreement among scientists that a single, sharply defined event happened on one exact date that we can call 10,300 BC. What the evidence actually supports is something a little different, and honestly, a little more interesting. There's a broader era spanning roughly from around 14,000 years ago to about 8,000 years ago, during which global sea levels rose dramatically, and at certain points within that era extremely fast. Researchers have identified several distinct pulses within this broader era, each associated with different ice sheets collapsing or draining at different times. Some studies place a major pulse close to the date we're using as our anchor point tonight. Other studies place similar pulses earlier or later, sometimes by 1,000 years or more. The name 10,300 BC works well as a focal point for our investigation, because it sits near one of the more well-supported candidates for extremely rapid sea level rise. But you should think of it less like a single dramatic headline and more like a spotlight we're shining onto one particularly intense chapter within a much longer, messier story. Alright, now let's arm ourselves with some vocabulary, because these next terms are going to come up constantly, and getting them straight now will save a lot of confusion later. First, meltwater pulse. This refers to a relatively short period of time during which massive quantities of fresh water, previously locked away as glacial ice, drain rapidly into the ocean. This can happen through several mechanisms: ice sheets melting from warming temperatures, ice dams holding back enormous glacial lakes suddenly failing and releasing all that water at once, or ice sheets becoming unstable and collapsing into the sea in massive chunks. A meltwater pulse is essentially a geological term for water rushing into the ocean faster than the normal gradual pace of melting would suggest. Second, eustatic sea level rise. This is a slightly technical term, but it's crucial. Eustatic refers to changes in sea level that happen globally, caused by an actual change in the total volume of water in the world's oceans, or changes in the shape of the ocean, basins themselves. When ice melts and that water flows into the sea, that's eustatic sea level rise. It affects the entire planet's oceans roughly equally, at least in theory. Third, local relative sea level. This is where things get more complicated and honestly more human. Even though eustatic sea level rise happens globally, the actual sea level experienced at any particular coastline can be very different from place to place. Why? Because land itself moves. Some coastlines are sinking due to tectonic activity, or the slow settling of the crust after the weight of ice sheets was removed, a process called isostatic adjustment. Other coastlines are actually rising for similar reasons. So a location that was heavily weighed down by an ice sheet for thousands of years might spring back upward once that ice melts away, partially offsetting the rising ocean. Meanwhile, a location far from any ice sheet might sink slightly as the crust readjusts to that same meltwater, redistributing weight across the globe. This means the same global meltwater pulse could have drowned one region rapidly while barely affecting another 1,000 miles away. And finally, inundation. This is simply the process of land being submerged by rising water. But it's worth pointing out that inundation isn't necessarily instant, even during a meltwater pulse. A gently sloping coastal plain might see the water's edge creep inland by miles, with only a small rise in sea level, while a steep coastline might barely change at all with the same rise. This is one of the reasons flat, low-lying regions like the ones we're going to explore later in this series, places like Doggerland and Sundaland, were so vulnerable. Even a modest, sustained rise in sea level could translate into an enormous visible retreat of dry land, potentially within a human lifetime. So keep these 4 ideas in your mind as we move forward. Meltwater pulse, eustatic rise, local relative sea level, inundation. Because the real mystery we're chasing isn't just whether the water rose, it's how fast it rose in specific places where people were actually living, and whether that speed was enough to turn a slow environmental shift into a sudden lived catastrophe. To understand that, we need to go back even further, to the ice itself, and the almost unimaginable amount of frozen water sitting on top of entire continents, just waiting for the conditions that would set it free. Picture the planet at the height of the last ice age. Not just colder than today, different. So different that if you could stand on a familiar coastline and look out toward the horizon, you might not see an ocean where you expect one. You might see a plain, a river, grassland, forest, herds of animals moving across land that is now buried beneath 100 meters, sometimes more, of seawater. That is the world before the water. At the last glacial maximum, roughly 26,000 to 19,000 years ago, an almost unimaginable quantity of Earth's water was locked up as ice on land. Not floating sea ice, which doesn't significantly change sea level when it melts. We're talking about continental ice sheets. Mountains of frozen water piled over North America, Northern Europe, and parts of Asia. Ice thousands of meters thick in places, so heavy it pushed the Earth's crust downward beneath its weight. Estimates vary, because nothing about reconstructing an ice age is simple, but the basic picture is solid. Global sea level was somewhere around 120 meters lower than it is today. Maybe a little more in some reconstructions. That's nearly 400 feet. The vertical height of a 30-story building. Now, 120 meters might not sound like much when you say it quickly. But sea level doesn't just move upward and downward on a map like a bathtub filling. Coastlines are usually shallow slopes, push the shoreline down by 120 meters, and in many parts of the world, the sea retreats not by a few yards but by tens, sometimes hundreds of miles. And that exposed land wasn't empty. It included continental shelves, the broad, shallow platforms around continents that are underwater today. It included river valleys that continued far beyond modern coastlines. It included wetlands, estuaries, lakes, dunes, forests, and open plains, places where fresh water gathered, places where fish spawned, places where birds migrated, places where large animals came to drink. In other words, exactly the kinds of landscapes humans tend to notice, return to, and eventually build their lives around. Today we think of the coast as the edge of the world. During the Ice Age, the modern coast was often nowhere near the edge. It was an inland line on a much larger continent. Take Britain. Today it sits offshore from mainland Europe, separated by the English Channel and the North Sea. But for much of the last Ice Age, Britain was not an island at all. You could walk from what is now England into what is now France, Belgium, the Netherlands, Denmark, and beyond. The North Sea basin was largely dry land, crossed by rivers and occupied by animals and people. The English Channel, in its modern form, was not the permanent marine barrier we know today. Or look at Southeast Asia. Modern maps show Indonesia as a vast chain of islands scattered between mainland Asia and Australia. But when sea level was lower, many of those islands were connected. The Malay Peninsula, Sumatra, Java, Borneo, and huge areas of what is now the shallow Java Sea formed part of a single sprawling landmass called Sundaland. It was larger than many modern nations. Rivers ran across plains that have now vanished beneath tropical water. Even Australia and New Guinea were connected by a broad landmass called Sahul. The Persian Gulf, now a shallow arm of the Arabian Sea, was largely exposed as a river basin. The Bering Strait between Siberia and Alaska was dry land, creating Beringia, a vast region linking Asia and North America. Across the world the map had been redrawn, and it had been redrawn by ice. The largest player in this frozen global system was the Laurentide ice sheet. This was the giant sitting over North America. At its maximum extent, it covered most of Canada and spread deep into what is now the northern United States. Imagine an ice cap stretching from the Arctic across the Great Lakes region and into New England, the upper Midwest, and the northern Great Plains. In some areas, it was 2 to 3 kilometers thick, a wall of ice so massive that it reshaped entire drainage systems, scraped bedrock, created thousands of lakes, and altered weather patterns across a continent. To the east and across the Atlantic was the Fennoscandian ice sheet, sometimes grouped into the broader Eurasian ice complex. It covered much of Scandinavia, Finland, the Baltic region, and parts of northern Europe. Britain itself was partly glaciated, especially in the north. Further east, smaller but still important ice masses occupied parts of Russia and the Arctic islands. Then there was Antarctica. Antarctica was already frozen, of course, but during the last glacial maximum its ice sheets expanded outward, extending farther across the continental shelf than they do today. And scattered across high mountain ranges around the world were thousands of smaller glaciers and ice caps. In the Alps, the Himalayas, the Andes, the Rockies, Patagonia, New Zealand, Alaska, East Africa. Each one may have been tiny compared with Laurentide or Fennoscandian ice, but together they stored an enormous amount of water. This is the key thing to understand. The oceans had not disappeared. They had been drained into the continents, not literally drained through pipes, obviously. But over tens of thousands of years, snowfall accumulated in cold regions faster than summer melting could remove it. Snow became ice. Ice became glaciers. Glaciers merged into ice sheets. And every snowflake that stayed frozen on land was, in effect, a tiny amount of water removed from the sea. Over millennia, those tiny withdrawals added up to an ocean nearly 120 meters lower than ours, which meant the planet's coastlines were radically different. Not slightly adjusted, radically different. The Gulf Coast of North America extended far beyond modern Texas and Florida. The Yellow Sea between China and Korea was largely dry land. The Persian Gulf was not a gulf. Huge portions of the modern North Sea, Java Sea, Arafura Sea, and Bering Sea were landscapes people could walk across. River systems reached across these exposed shelves, often joining together into much larger drainage networks before finally reaching the distant ocean. Think about what that means for ancient human movement. We tend to imagine prehistoric migrations as people crossing the maps we know today, crossing straits, boarding boats, skirting coasts. But the maps were different. A journey that looks like an ocean crossing to us may have been a walk across lowland grassland to them. A place that is now an isolated island may have been a hill overlooking a river valley. A modern fishing ground may have been a hunting ground. And because coastal zones are among the richest environments on Earth, these lost landscapes were probably attractive places to live. Not every exposed shelf would have been paradise. Some were cold, dry, windy, or seasonally harsh. But many contained rivers, marshes, game, edible plants, shellfish along the shifting shore, and access to both land and water resources. They were ecological crossroads. Humans had been exploiting coastlines long before the end of the Ice Age. They gathered shellfish, caught fish, hunted waterfowl, travelled along rivers, and used shorelines as routes between regions. But the archaeological record gives us a distorted picture, because the places most likely to preserve evidence of long-term coastal life are now underwater. The campsites, the hearths, the burials, the tool workshops, the places where families returned season after season. Many may lie beneath the North Sea, beneath the Persian Gulf, beneath the Sunda Shelf, beneath the continental shelves of Africa, India, the Americas and Australia. That doesn't mean every drowned plane hid a lost city. We need to be careful with that word. For 10,300 BC, most human societies were still hunter-gatherers or beginning more intensive local ways of managing wild resources. The evidence for true cities with dense populations, monumental architecture and state-level organisation comes much later in most regions. But a settlement does not have to be a city to be deeply important. A village can be lost, a seasonal gathering place can be lost, a sacred landscape can be lost, a river crossing, a burial ground, a fishing camp, a whole territory remembered by generations can disappear beneath the sea without leaving a visible trace on land. And as the ice began to melt, that was exactly what started to happen. The frozen water did not return to the ocean evenly. It came in stages, sometimes slowly enough that coastlines shifted over centuries. Sometimes, perhaps, quickly enough that people living on low flat ground would have watched familiar marshes become tidal creeks, watched freshwater valleys turn brackish, watched the horizon move inland year by year. Before we can ask how fast that happened around 10,300 BC, though, we need to ask a harder question. How can anyone possibly know where the sea was 12,000 years ago, let alone how quickly it rose? The short answer is, they don't know from one single measurement. There is no ancient tide gauge sitting on a beach from 12,000 years ago, with a neat little chart showing the water climbing day by day. What scientists have instead is a global detective story. Thousands of clues scattered across coastlines, reefs, caves, marshes and ocean floors. Each clue tells part of the story. Put enough of them together, compare their dates, correct for the movement of the land itself, and a picture begins to emerge. Not a perfect picture, not a movie with every frame intact. More like a time-lapse assembled from damaged photographs. But the overall pattern is clear enough to tell us something extraordinary happened as the Ice Age ended. One of the most useful clues comes from coral. Corals are not just colourful organisms growing in tropical water. Some species are extremely picky about where they live. They need sunlight. They need warm water. And crucially, they grow within a relatively narrow depth range below the sea surface. If you find an ancient coral reef now sitting far below modern sea level, that reef can tell you where the sea surface was when the coral was alive. Imagine a coral growing near the surface 14,000 years ago. Today, divers find that same coral terrace 80 or 100 meters underwater. The coral did not decide to move downward. The ocean rose above it. In places like Barbados, Tahiti, the Bahamas, and the islands of the Western Pacific, scientists have found sequences of drowned reefs. Each one is like an old shoreline preserved in limestone. Coral grows upward toward the light as water rises. But if sea level rises too quickly, the reef can drown. It ends up stranded in deeper water, a fossil snapshot of a changing sea. These reefs are especially valuable because corals can be dated with remarkable precision using uranium-thorium dating. Here's how that works. When coral grows, it incorporates tiny amounts of uranium from seawater into its skeleton. Uranium is radioactive. Over time, it slowly changes into thorium at a known rate. Since living coral takes in uranium but almost no thorium, scientists can measure the ratio between the two and calculate how long it has been since that coral formed. It is a geological clock, and for the period around the end of the last ice age, it can often provide dates accurate to within decades or centuries under good conditions. That is incredibly precise when you're looking back more than 12,000 years. But corals are only one part of the puzzle. Much of the evidence comes from mud. That may not sound dramatic. No giant lost temple. No ancient inscription saying, "The sea reached this point in the year 10,300 BC." Just layers of sediment. Sand, silt, clay, pollen, shell fragments, peat, microscopic organisms. But coastal mud is a kind of environmental archive. Every layer records the conditions that existed when it was deposited. Take a salt marsh. A marsh does not grow at just any elevation. Different plants and tiny organisms live at different heights relative to the tides. Some thrive just above high tide. Others live in salty mud regularly flooded by seawater. Others appear only in freshwater wetlands beyond the reach of the tides. When sea level rises, those environments move inland. A freshwater peat layer may be buried by brackish mud. That mud may be covered by tidal flat sediment, then perhaps by fully marine sand, containing shells from the open coast. In one vertical core of sediment, scientists can watch a landscape being overtaken by the sea. They drill down, they bring up a cylinder of mud, and they read it from bottom to top like a history book. Mangroves can tell a similar story in tropical regions. Mangrove forests occupy a narrow ecological zone along coasts and estuaries. Their roots, pollen, and peat can reveal whether an area was once a sheltered shoreline, a tidal swamp, or dry land beyond the reach of salt water. If old mangrove peat is now submerged offshore, it can mark where sea level used to be. Then there are caves. Caves seem like the last place you would look for evidence of ancient oceans. But coastal caves can preserve mineral deposits called speleothems. Stalagmites, stalactites and flowstones form when fresh water drips through air-filled caves. They cannot grow underwater, so if you find a stalagmite deep inside a submerged cave, it tells you the cave was dry when that mineral formed. Sea level had to be lower than the cave entrance at that time. In some places, caves contain another kind of evidence, mineral crusts that form near the boundary between fresh groundwater and seawater. As sea level changes, that underground boundary shifts too. These deposits can preserve a record of old shorelines hidden beneath the surface. And then there are microfossils, tiny organisms often smaller than a grain of sand that most people never think about. Foraminifera, for example, are microscopic shelled creatures that live in oceans, estuaries and salt marshes. Different species prefer different salinities, depths, temperatures and tidal elevations. Find their shells in a sediment core and you can reconstruct what kind of water was there when that layer formed. A core might show freshwater plants at the bottom, then salt marsh foraminifera, then species that prefer tidal flats, then fully marine species. The exact sequence tells scientists that the sea did not simply appear out of nowhere. It advanced, changing the landscape step by step. To turn these environmental clues into a timeline, researchers need dates. Radiocarbon dating is one of the main tools. Living plants and animals absorb carbon, including a tiny radioactive form called carbon-14. When they die, that carbon-14 begins to decay. Measure what remains in a piece of peat, a shell, charcoal from an ancient fire, or preserved wood from a drowned forest, and scientists can estimate its age. Radiocarbon dating is powerful, but it comes with complications. The amount of carbon-14 in the atmosphere has changed over time, so raw radiocarbon ages have to be calibrated against independent records. Marine organisms can also appear artificially old because the ocean contains carbon that has been circulating for centuries or even millennia. This is called the marine reservoir effect. Date a shell without correcting for that effect, and you may get a misleading result. So scientists compare methods. Radiocarbon dates from peat. Uranium-thorium dates from corals, ages from cave minerals. Volcanic ash layers where available, ice core records. Sediment sequences. The strongest reconstructions are not built on one line of evidence. They are built where multiple lines converge, but even then, every sea level curve comes with uncertainty. First, timing. A date may have an error range of 50 years, 100 years, sometimes more. That matters enormously if you're trying to determine whether a rise took place over a century, 2 centuries, or a millennium. Then there is elevation. Measuring the depth of an ancient reef or peat layer sounds simple until you remember that coastlines are constantly being reshaped. Waves erode. Sediment compacts. Faults move. Storms redeposit material. A peat bed might have formed slightly above sea level, not exactly at it. A coral may have grown a few meters below the surface, not right at the tide line. And then comes the complication that changes everything. The land itself moves during the Ice Age. Giant ice sheets press down on the crust with unimaginable weight. North America and Northern Europe were not just covered in ice. They were physically pushed downward by it. When the ice melted, the weight was removed. The land began to rebound upward, slowly springing back like a mattress after someone gets out of bed. Scientists call this glacial isostatic adjustment, GEA for short, and it is still happening today. In parts of Scandinavia, land is still rising by several millimeters a year because the crust is recovering from Ice Age ice. In some areas, ancient shorelines now sit high above modern sea level. Not because the ocean fell, but because the land rose. Other places experienced the opposite. Regions around the edges of former ice sheets, the so-called forebulge areas, had been pushed upward when nearby crust sagged under the ice. After deglaciation, those regions began to sink back down. Parts of the east coast of North America are still affected by this process. So are low-lying areas around the North Sea, which means a shoreline record from Sweden, Britain, Florida, Barbados, or Southeast Asia may all be recording different combinations of the same global ocean rise and local vertical land movement. This is why scientists distinguish between global mean sea level and relative sea level. Global mean sea level is the average change in the volume of the oceans worldwide. It is the big planetary signal created when land ice melts and adds water to the sea. Relative sea level is what people at a particular coast actually experience. It is the position of the water relative to the land beneath their feet. And those can be very different things. If global sea level rises by 10 meters, but your land rises by 8 meters because the crust is rebounding, your local shoreline may appear to rise by only 2 meters. If your land is sinking at the same time, the local rise may be much greater. Add tides, storms, changing river sediment, shifting currents, and regional differences in gravity caused by the melting ice sheets themselves, and the simple idea of one uniform rising ocean begins to break apart. There was no single coastline experience. There were thousands. For people living on a flat, slowly sinking coastal plain, even a modest global rise could transform the world. Rivers would back up. Marshes would become estuaries. Salt water would move into freshwater wells. The shoreline might retreat miles inland. But somewhere else, near a rebounding former ice sheet, the same global event could look less dramatic. The sea might advance slowly, pause, or even appear to retreat relative to the rising land. So when researchers say sea level rose rapidly around the end of the Ice Age, they are not claiming every beach on Earth vanished at the same rate on the same day. They are describing a global process reconstructed from many imperfect local records. A process powerful enough to redraw continents, but complicated enough that every coast tells the story differently. And once scientists began matching those records against the history of melting ice sheets, they realized something else. Sea level had not risen at one smooth, gentle pace. At certain moments, the evidence suggests, the ocean surged. But what does that actually mean? How can an ocean surge? The first image most people imagine is simple. The planet warms, ice melts, water runs downhill into the sea, sea level rises, and yes, at the broadest level, that is exactly what happened. But it misses the machinery. Ice sheets are not just giant piles of frozen water sitting still on the landscape. They are dynamic systems. They flow. They fracture. They collapse at their edges. They hold back lakes the size of modern seas. And when one part of the system fails, it can trigger changes far beyond the original break. Think of an ice sheet less like a block of ice in a freezer, and more like an extremely slow river under pressure. At the height of the last ice age, enormous ice sheets covered northern North America and northern Europe. In some places the ice was kilometres thick. Its own weight pushed it outward from the centre, inch by inch, year after year. Snow accumulated on top, ice compacted beneath it. Gravity pulled the mass toward lower elevations and eventually toward the ocean. As long as snowfall at the top roughly balanced melting and ice loss at the edges, the sheet could remain relatively stable. Not motionless, never motionless, but stable enough that its total size changed slowly. Then the climate warmed. Warmer summers increased surface melting. Rain fell on ice that would once have stayed frozen. Dark dust, rock debris, and meltwater pools absorbed more sunlight than clean snow, heating the surface further. This is called the albedo effect. Fresh snow reflects sunlight back into space. Dark, wet ice absorbs it. Once the white surface begins disappearing, melting can accelerate. But the most dramatic changes often happened at the margins, where ice met the ocean or terminated in huge lakes. This is where calving enters the story. Calving is the process by which chunks of ice break away from the front of a glacier or ice sheet and become icebergs. Everyone has seen the basic idea. A towering wall of ice fractures, collapses, and sends blocks crashing into the water. But on an ice sheet scale, calving is not just a spectacular local event. It can remove the barrier holding back vast volumes of inland ice. A glacier flowing into the sea may develop a floating extension called an ice shelf. That shelf can act like a brake. It presses against islands, seabed ridges, and the walls of fjords, slowing the flow of ice behind it. Remove the shelf through warming, thinning, or repeated calving, and the inland glacier can speed up. The brake comes off, and when an ice stream speeds up, the consequences can be enormous. Ice streams are fast-moving corridors within an ice sheet. While much of the surrounding ice may creep along slowly, an ice stream can carry ice toward the coast at dramatically higher speeds. They are like express lanes in a frozen highway system. Some are lubricated by water at their base. Some flow over soft waterlogged sediments. Some are channeled through low areas in the bedrock beneath the ice. If warming, rising sea level, or changes in meltwater allow one of these corridors to accelerate, it can drain a huge inland reservoir of ice much faster than normal. Not all at once, not in a single afternoon, but fast enough to matter on the scale of human societies living along low coasts. And there is another problem. Much of an ice sheet can sit below sea level. That sounds impossible at first. How can ice on land be below the ocean surface? Because the weight of the ice pushes the crust downward. In places such as West Antarctica today, the bedrock beneath the ice slopes inland and lies far below sea level. Similar conditions existed along parts of the retreating ice age, ice sheets. This creates what scientists call marine ice sheet instability. Here is the basic mechanism. Imagine the edge of an ice sheet resting on bedrock below sea level. If warm ocean water reaches that edge, it melts the ice from underneath. The grounding line, the point where the ice stops resting on the seabed and begins floating, retreats inland. But if the bedrock slopes deeper inland, the retreating ice edge moves into deeper water. Deeper water means a thicker ice front. A thicker ice front can flow faster. Faster flow draws down more ice from the interior. That causes further retreat. The process can feed on itself. It is not guaranteed. Bedrock ridges can slow or stop it. Colder conditions can stabilize it. Ice sheets are complicated, and scientists still debate exactly how these mechanisms operated during particular ancient events. But the physics is real. Once a vulnerable ice margin begins retreating, it can cross a threshold where gradual warming produces a much less gradual response. Then there were the lakes. As ice sheets retreated across North America, they often blocked natural drainage routes. Meltwater poured off the ice, but instead of flowing freely to the sea, it pooled against the ice margin. The result was a series of enormous proglacial lakes formed in front of glaciers. Some were vast. Lake Agassiz, for example, at different times, covered an area larger than all of the modern Great Lakes combined. It was not a peaceful blue lake bordered by forests and holiday cabins. It was an unstable reservoir trapped between melting ice, shifting land, and changing drainage channels. A lake like that can drain gradually as rivers cut new outlets, or it can drain abruptly when an ice dam fails, when retreat opens a lower escape route, or when water overtops a barrier and begins eroding it away. This is the difference between sustained ice loss and an abrupt drainage event. Sustained ice loss is the long game. Warmer conditions cause an ice sheet to lose more mass than it gains, year after year, century after century. The ocean receives a persistent extra supply of water. Sea level rises over a long interval, perhaps unevenly, perhaps with pauses and accelerations, but driven by an ongoing imbalance in the ice system. An abrupt drainage event is more like pulling the plug from a reservoir. A proglacial lake may release a huge volume of fresh water over years, months, or potentially even shorter intervals in extreme cases. The flood would be catastrophic near its source, tearing through river valleys and reshaping landscapes. But even a massive flood does not necessarily raise global sea level by meters overnight. The ocean is too large. A single drainage event may leave a clear regional scar while contributing only a limited amount to global sea level. A true meltwater pulse is usually something bigger, a period when ice sheets, glaciers, and sometimes lake drainage systems collectively delivered water to the ocean at an unusually rapid rate. The word pulse makes it sound instantaneous, a heartbeat, one sudden jump. But in sea level science, a pulse is generally measured over centuries. Sometimes perhaps a few centuries, sometimes longer. The geological record is rarely precise enough to tell us whether every meter of rise occurred smoothly, in bursts, or in a sequence of separate episodes within that interval. Individual glacier collapses could be fast. Individual lake outbursts could be faster still. A local shoreline might shift dramatically after a storm surge, a river flood, or the breaching of a coastal barrier. But the global ocean does not climb 10 meters between breakfast and sunset. Its overnight rise is usually overnight in geological terms, fast enough to transform coastlines within many human lifetimes, fast enough for grandparents to remember dry hunting grounds where their grandchildren knew only tidal water. But not usually a single worldwide wall of water arriving on one date. And the fresh water did more than raise the sea. Where that water entered the ocean mattered. The North Atlantic is driven in part by a vast circulation system involving warm surface water moving northward, cooling, becoming saltier and denser, then sinking into the deep ocean. This sinking helps power a global pattern of ocean circulation, often called the Atlantic Meridional Overturning Circulation. Add enough cold fresh water to the North Atlantic, and you dilute the surface water. Fresher water is less dense. It is less likely to sink. That can weaken parts of the circulation system, changing how heat moves around the planet. The exact response depends on how much water arrived, where it entered, and how quickly. Researchers are still working through those details. But ice core records and ocean sediments show that the end of the Ice Age was not a simple steady warming trend. It was a climate system lurching between warmer and colder phases, with sudden shifts that could unfold within decades. So a melting ice sheet could do two things at once. It could raise the oceans globally while its freshwater disrupted circulation, enough to cool parts of the North Atlantic region. More melt, more fresh water, A weaker ocean conveyor, changing rainfall, shifting storm tracks, different temperatures across entire continents. This was not one machine. It was a network of machines, all connected, ice margins breaking apart, fast-moving ice streams draining inland ice, lakes searching for new outlets, oceans absorbing the water, currents responding to the fresh water, and climate feeding back into the ice. And somewhere in that unstable world, around the boundary of 10,300 BC, scientists see signs that the pace may have changed again. But before we follow that signal into the rocks, we need to deal with the phrase at the centre of this whole story. Sea levels rose overnight, did they? The honest answer is both more complicated and, in some ways, more unsettling. No evidence shows the entire global ocean suddenly climbing by several meters between one sunset and the next. There was no single night when every beach on Earth vanished beneath a planet-wide wall of water. The oceans are simply too vast. Even an enormous discharge of meltwater has to spread through connected basins, move around continents, adjust to winds, tides, currents, and the shape of the seafloor. But that does not mean the experience was slow, gentle, or easy to ignore. Overnight depends on who is telling the story. To a geologist studying sediment layers thousands of years later, a century can look almost instantaneous. A layer of peat, soil, shells, or coastal mud may represent decades, centuries, sometimes longer. If the shoreline moved inland during that interval, the record may preserve a sharp boundary. Dry land below, tidal sediment above. It can look like a switch was thrown, and for people living through it, a rise spread across generations could still feel like a disaster arriving all at once. Imagine a low coastal plain. It slopes so gradually that you can walk for miles and gain almost no elevation. A 1 meter rise in sea level does not just move the shoreline 1 meter inland. It can move it hundreds of meters, sometimes kilometers, depending on the landscape. Now add tides. A coast that remains dry at low tide may begin flooding twice a day at high tide. Salt water reaches the marshes. Freshwater ponds turn brackish. Plants die. Fish move into places where people once hunted deer. Wells become salty. Storms push water farther inland than anyone remembers. For a family living there, the decisive change may not be the average sea level itself. It may be the first season when the spring tides no longer retreat. The first storm that crosses a barrier beach. The first year the old camp cannot be used because the ground has turned into mud. That can feel overnight. And there is another problem with the phrase sea level. It makes the ocean sound like one simple measuring line, rising evenly everywhere at exactly the same rate. It is not. Global mean sea level is an average. It tells us in broad terms how much water has been added to the oceans or how ocean volume has changed. But local relative sea level is what people actually experience. And local sea level can rise faster, slower, or even fall depending on what the land itself is doing. At the end of the Ice Age, this mattered enormously. Land beneath the great ice sheets had been pushed down by kilometres of ice. As the ice melted, the crust began slowly rebounding upward. In parts of Scandinavia and Canada, that rebound was so strong that local shorelines could appear to retreat even while global sea level was rising. But farther from the former ice sheets, the opposite could happen. As the heavy ice disappeared, surrounding regions flexed and tilted. Some coastal areas sank relative to the ocean. Sediments compacted. River deltas shifted. Wetlands collapsed. In those places, the sea could seem to advance faster than the global average predicted. Then there are events that have nothing to do with a long-term change in ocean volume, but can be just as devastating locally. A storm surge can drive seawater far inland in a matter of hours. A tsunami can cross an ocean and strike a coast with almost no warning. A river flood can drown an estuary. An earthquake can drop coastal land by meters in minutes. A glacial lake outburst can send a wall of fresh water through a valley, stripping soil, forests, animals and settlements from the landscape. All of these can leave dramatic flood deposits, and that creates a challenge for scientists. When they find marine sand above older soil or shells in an unexpected layer, they have to ask, was this a gradually rising shoreline, a giant storm, a tsunami, land subsidence, a single flood, or several different processes stacked on top of each other? The answer is rarely written in one perfect layer. That is why ancient sea level reconstruction is difficult. We do not have tide gauges from 12,000 years ago. No one stood on a cliff in 10,300 BC, marking the waterline on a stone wall. Scientists have to reconstruct the past from indirect evidence. Coral reefs that grew near sea level, mangrove peat that formed in tidal zones, drowned river valleys, cave deposits, shells, sediment chemistry, and the changing positions of ancient shorelines. Each record has limits. A coral may tell us where sea level was when it grew, but dating can carry uncertainty. A peat bed may show when salt water reached a marsh, but not whether the transition took 10 years or 100. Sediments can be disturbed by burrowing animals, waves, later erosion, and changing currents, and different coastlines respond differently to the same global event. So when researchers describe a meltwater pulse, they are usually not claiming to see every year of change. They are identifying an interval when the evidence suggests sea level rose unusually fast, compared with the background trend. Maybe several meters over a few centuries. Maybe a sequence of jumps and pauses. Maybe rapid global rise combined with local subsidence, high tides, storms, and collapsing coastal barriers that made the final transformation far more dramatic in certain places. That distinction matters because the literal image is misleading. It suggests one universal flood, one date, one wave, one moment when every coastal society looked up and saw the ocean coming. The real story may be stranger. The sea did not need to rise everywhere overnight to erase worlds within living memory. It only had to rise fast enough that each generation inherited a shoreline farther inland than the last. Fast enough that familiar hunting grounds became marsh. Marsh became tidal flat. Tidal flat became open water. And at certain vulnerable coasts, one storm, one surge, one breached barrier could turn a long-term rise into a single unforgettable catastrophe. So no, the whole planet probably did not flood in one literal night. But somewhere along the edges of the post-Ice Age world, people may have gone to sleep beside land their parents knew, and woken to find that the sea had finally claimed it. If there was a period when the sea began taking land faster than people could adapt, where would we see it? Not in a single giant line drawn across the planet. We would see it in fragments, a coral reef in the Caribbean that stopped growing at one depth and resumed higher up, a drowned peat bed beneath the North Sea, saltwater mud laid over an old freshwater marsh, river valleys cut when sea level was low, then filled with marine sediment as the ocean moved inland, shorelines abandoned, then buried, then preserved beneath meters of sand and mud. And when scientists compare those fragments, something interesting appears. The end of the last ice age was not one smooth, steady climb from low sea levels to modern coastlines. It was more like a staircase, long intervals of rapid rise, shorter pauses, sudden accelerations, regional complications. The overall direction was unmistakable. The ocean was rising. But the speed changed. Around 10,300 BC, or roughly 12,000 years ago in calendar terms, researchers identify one of these potentially important intervals. The date itself needs some care. Ancient dates are not as precise as dates in a history book. Different studies use different dating methods, different calibration curves, and different definitions of what counts as a pulse. One researcher may say 12,200 years ago. Another may place the same event centuries earlier or later. And because years before present conventionally means before 1950, converting that number into BC can make the labels look even more confusing. But broadly speaking, the period around 12,000 years ago sits in a dramatic phase of deglaciation. Ice sheets were still melting. The great continental glaciers had not yet vanished. Massive volumes of water were entering the oceans, and sea level, already rising for thousands of years, may have accelerated again. This is often discussed in connection with named meltwater pulses. The most famous is Meltwater Pulse 1A, an enormous acceleration around 14,600 years ago. In some reconstructions, global sea level rose by more than 10 meters in only a few centuries. That is the kind of event that makes geologists sit up straight. Not because it means the whole world drowned in a day, but because a rise of that scale would redraw coastlines within a handful of human lifetimes. Then there is Meltwater Pulse 1B. This one is harder. Some records suggest another phase of unusually rapid sea level rise, beginning around 11,500 years ago, possibly extending into the period close to 10,300 BC. Other reconstructions break that rise into smaller pulses. Others argue that the evidence does not support one globally synchronized event at all. Instead, they see a complicated sequence of ice sheet collapses, ocean adjustments, and regional shoreline changes spread across centuries. That disagreement is not a weakness in the science. It is the science doing its job, because the Earth did not leave us one clean measuring stick. One of the strongest sources of evidence comes from tropical coral reefs. Certain corals grow close to sea level. If you find an ancient coral now submerged at a known depth, date it accurately, and understand the local geology, it can act like a tiny fossil tide gauge. Barbados in the Caribbean became famous for this. Its uplifted coral terraces preserve a record of changing sea levels through the last deglaciation. Far away, coral records from Tahiti and other tropical locations offer another view. These sites are separated by entire oceans. They experience different tides, currents, tectonic histories, and local land movements. So if they show broadly similar periods of rapid sea level rise, that is powerful evidence that something global was happening. And they do agree on the big picture. Sea level rose rapidly during deglaciation. It did not move upward at a constant rate. There were intervals when the rate increased sharply. The ocean was responding to major injections of meltwater from collapsing ice sheets. But agreement on the big picture does not mean agreement on every detail. Corals grow within a range of depths, not at one mathematically perfect elevation. Their ages carry uncertainties. Some reefs may have been altered by later erosion, storm damage, or tectonic uplift and subsidence. And translating a local coral depth into global mean sea level requires correcting for the changing shape of the Earth itself. That last part is especially strange. When a giant ice sheet melts, it does not simply add water to the ocean. It changes gravity. Ice sheets are so massive that they pull ocean water toward them. As the ice disappears, that gravitational pull weakens. Water redistributes. The seafloor flexes. Land near the old ice sheets rebounds upward. Land farther away can tilt or sink, so a coral in Tahiti and a drowned marsh in northern Europe may both record the same global meltwater event, but they may not record exactly the same local sea level rise. Then there are continental margins, the drowned edges of continents. Offshore, scientists find ancient river channels, peat layers, lagoons, beach ridges, and estuaries now buried beneath the sea. These records are often closer to the human landscapes that were being lost. They can reveal when a coastline shifted from forest or grassland to marsh, from marsh to tidal flat, from tidal flat to shallow sea. But they come with their own problems. A continental shelf is a violent place geologically. Waves erode it, rivers cut into it, storms rearrange sediment. Later sea level rise can destroy the very shoreline evidence scientists want to study. What survives may be incomplete, compressed, or displaced. Still, when coral records, drowned coastlines, and sediment cores from widely separated regions all point toward episodes of acceleration, the pattern becomes difficult to ignore. Around the time of 10,300 BC, the signal is real enough to take seriously. What remains uncertain is its exact shape. Was there one distinct global pulse? How many meters did sea level rise? Did the fastest phase last a few decades, a century, or several centuries? Which ice sheet supplied the water, the dying remnants of North American ice, Antarctica, Europe, or some combination of all of them? The answers are still being argued over, and that uncertainty matters. Because the difference between a 4-meter rise over 400 years and a 4-meter rise over 100 years is not just a technical detail. For a coastal community, it is the difference between adapting slowly and watching the map of your world change before your children grow old. To understand where that water may have come from, we have to go to the place where melting ice did not just raise the oceans. It reorganized an entire continent. North America was one of the places where the end of the Ice Age became almost unimaginably physical. For thousands of years, much of Canada and the northern United States had been buried beneath the Laurentide ice sheet. This was not a mountain glacier. It was a continental mass of ice, in places several kilometers thick, spreading from the Arctic southward into what are now the Great Lakes states and New England. At its maximum, the Laurentide held enough frozen water to lower global sea level by tens of meters. And by around 10,300 BC, it was dying. Not disappearing all at once. Not collapsing in one clean cinematic moment. The ice margin was retreating, pausing, advancing in places, breaking apart in others. Every summer, meltwater ran off its surface. Every season, rivers carried enormous loads of sediment away from its edge. And wherever the ice blocked a natural drainage route, water began to collect. That created lakes on a scale almost difficult to picture. Along the retreating edge of the Laurentide were vast proglacial lakes. Lakes formed because the ice itself acted like a dam. In places, the ice blocked northward flowing rivers and trapped water across lowlands that today are dry farmland, forest, or city. The most famous was Lake Agassiz. At various times, Lake Agassiz covered huge areas of central North America, spreading across parts of modern Manitoba, Ontario, Saskatchewan, North Dakota, and Minnesota. At its greatest extent, it was larger than all of the modern Great Lakes combined. Imagine standing on a shoreline in what is now North Dakota, looking out over an inland sea. No skyscrapers, no highways, no familiar map, just cold water stretching toward an ice wall on the northern horizon. And Agassiz was not alone. There were other ice margin lakes, constantly changing as the glacier shifted. Lake McConnell in the northwest, Lake Ojibwe farther east, smaller basins around the Great Lakes. Each one was controlled by a fragile arrangement of ice, rock, elevation, and water pressure. A retreating ice sheet could uncover a new outlet. An advancing tongue of ice could block an old one. A moraine, basically a wall of gravel and debris pushed up by the glacier, could hold water back for centuries. Then water levels would rise high enough to spill over a new divide. When that happened, the drainage of an entire lake system could be rerouted. And that is where the story stops being just about North America, because the direction of meltwater mattered. If lake water escaped southward, it could flow through the Mississippi system and enter the Gulf of Mexico. If it escaped eastward, it could move through the Great Lakes region and the St. Lawrence Valley, eventually reaching the North Atlantic. In other configurations, water may have found routes through river systems now altered, buried, or completely abandoned. The exact timing of each rerouting event is still debated. The ancient landscape has been reshaped by later rivers, forests, farms, cities, and thousands of years of erosion. And the ice margin itself was constantly moving, so scientists have to reconstruct these drainage pathways from abandoned channels, lake sediments, shorelines cut into hillsides, and strange deposits of sand and gravel left by water that no longer flows there. But the basic principle is clear. North America had become a giant plumbing system controlled by melting ice. And sometimes the pipes changed. That mattered because dumping fresh water into the ocean is not the same thing as simply raising sea level. The North Atlantic is driven by a vast system of currents that moves heat around the planet. Warm, salty surface water travels northward. In the far North Atlantic, it cools, becomes denser, and sinks. That sinking helps power a larger circulation system, sometimes called the Atlantic Meridional Overturning Circulation. It is one of the reasons Western Europe is far warmer than its latitude alone would suggest. But fresh water is lighter than salt water. Pour enough cold fresh water into the North Atlantic, and you can make surface waters less dense. That may interfere with the sinking process. It may weaken the circulation that carries heat northward. And during the last deglaciation, when the planet was already lurching between cold and warm phases, even a temporary disruption could have major climate consequences. This is not a simple on-off switch. The ocean is too complex for that. Different models produce different results. Some freshwater releases may have had limited effects. Others may have been large enough and delivered in the right place to alter circulation more seriously. But the possibility is important. A lake draining through the Mississippi might add fresh water to the Gulf. A lake draining eastward through the St. Lawrence could send that water much closer to the sensitive regions of the North Atlantic, where deep water formed. Same water, different route, different consequences. That is why geologists care so much about old spillways and drowned channels. They are not just trying to draw an ancient map. They are trying to understand whether a changing ice margin helped change the climate of the entire northern hemisphere. And while the ice was reshaping the interior, the ocean was advancing along North America's edges. During the Ice Age, the Atlantic coastline had been far offshore. The continental shelf, now submerged beneath the sea, was exposed land. Rivers crossed broad coastal plains before reaching the ocean. The Chesapeake Bay did not exist as a bay. It was part of a river valley. Delaware Bay, Long Island Sound, the estuaries of New England, the drowned river mouths along the Gulf Coast, all of these landscapes were transformed as sea level rose. The sea did not simply wash over a flat, empty surface. It entered valleys, it moved up river channels, it flooded low basins. It turned freshwater wetlands into brackish marshes, marshes into tidal flats, and tidal flats into open estuaries. Forests that had grown far from the old shoreline were drowned, leaving peat beds and tree stumps beneath modern waters. For people living on those coastal plains, the loss would have come in stages. A fishing ground altered by salt water, a familiar crossing becoming tidal, a river mouth widening every generation, land that once supported camps, hunting routes, and seasonal gathering places becoming mudflat, then shallow bay, then sea. But North America adds one more twist. Near the old Laurentide ice sheet, relative sea level did not always rise in the same way it did elsewhere. The weight of the ice had pushed the land down beneath it and bulged land upward around its edges. As the ice melted, the buried land began to rebound. In some northern areas, land rose faster than the sea, making local shorelines appear to fall. Farther away, the effects could be very different. So there was no single North American experience of the rising ocean. There were drowned southern plains, changing Atlantic estuaries, shifting Great Lakes outlets, and northern coasts warped by the slow rebound of the earth itself. A continent was melting, draining, rising, sinking, and changing its rivers at the same time. And across the Atlantic, another lowland world was facing the sea. A world connecting Britain to Europe, where hunters crossed open plains that would eventually become the floor of the North Sea. Across the Atlantic, the same rising water was transforming a place that does not even appear on modern maps. Today, the North Sea separates Britain from Denmark, Norway, the Netherlands, Germany and Belgium. We think of it as a permanent feature of Europe, a cold grey stretch of water crossed by ferries, oil platforms, cargo ships and fishing boats. But around 10,300 BC, much of its southern and central basin was not sea. It was land, not one smooth, featureless plain, not an empty bridge between Britain and the continent. It was a huge, low-lying world of rivers, shallow lakes, marshes, gravel ridges, woodland, open grassland and seasonal wetlands. Britain was still connected to mainland Europe. A person could walk east from what is now eastern England into territories that would eventually lie beneath the North Sea, then continue toward the lowlands of modern Denmark, the Netherlands, or Germany. The coastline was far away. Exactly how far depended on the date, the local elevation, and the complicated movements of the land itself. But during the later stages of the Ice Age, sea level was still tens of meters lower than today. That exposed enormous areas of continental shelf. In the south, river valleys crossed terrain that is now underwater. In the centre, broad lowlands stretched across what would become the shallow North Sea. Farther north, deeper parts of the basin remained flooded earlier, and the retreating Scandinavian ice sheet still dominated the horizon. This was a landscape caught between worlds. To the north and east, ice still covered much of Scandinavia. To the south and west, forests and grasslands were expanding as the climate warmed. Herds moved through the changing terrain. Red deer, wild cattle, elk, boar, and smaller game would have found food along the edges of wetlands and woodland. Fish filled rivers and lakes. Waterfowl gathered in the marshes. Shellfish and coastal resources became available wherever the sea had begun pushing into the lowest valleys. For Mesolithic hunter-gatherers, this was not marginal land. It was potentially some of the richest land in northern Europe. Think about what people need if they are living without farms, cities, or stored grain. They need reliable water. They need animals moving through predictable routes. They need wood for fires and shelters. They need stone, plant foods, fish, birds, and places where different environments meet. Wetlands are especially valuable because they concentrate life. A narrow strip between forest, river, and marsh can provide more resources than a huge area of uniform land. And the North Sea lowlands had those boundaries everywhere. Rivers flowed across the exposed basin, carrying water from Britain and continental Europe toward the distant ocean. The Thames did not end in the modern Thames estuary. The Rhine did not reach the sea at Rotterdam. The Scheldt, Meuse, Elbe, and other river systems followed routes that were later drowned, merged, diverted, or buried beneath sediment. In some reconstructions, several of these rivers combined into major channels crossing the basin. Their valleys would have been landmarks in a world with no written maps. Places to camp, places to cross, places where fish moved upstream and herds came down to drink. Places where one community might encounter another after weeks of travel. But this landscape was never stable for long. Sea level was rising globally as ice sheets melted. At the same time, the land beneath northern Europe was moving. During the Ice Age, the enormous weight of Scandinavian ice had pressed the crust downward. Areas around the ice sheet were warped upward or tilted in response. When the ice began to disappear, the land started adjusting back. This process, called isostatic rebound, is still happening in parts of Scandinavia today. That meant relative sea level. The sea level people actually experienced on a particular coast could vary dramatically from place to place. In parts of northern Scandinavia, land uplift could keep pace with, or sometimes outstrip, the global rise of the ocean. Former shorelines ended up stranded high above modern sea level. But farther south, in the North Sea basin, and around the southern British and continental coasts, the opposite was often true. The land was lower, subsiding, or simply not rising fast enough. There the ocean advanced, and it did not advance in a neat line. A rising sea entered river valleys first. It turned freshwater channels into tidal creeks. It flooded low basins and created estuaries. It pushed salt water into wetlands that had supported reeds, peat, birds, and grazing animals. A familiar valley could become a marsh could become a tidal flat could disappear beneath shallow water. Meanwhile, changing rivers were reshaping the land from the other direction. As glaciers retreated, meltwater routes shifted. Sediment loads changed. Lakes formed and drained. Rivers cut new channels or abandoned old ones. So the people living in this lowland world were dealing with more than a coastline moving inland. Their entire network of water, food, travel routes, and seasonal camps was being rearranged. We know this world existed because the seabed has preserved fragments of it. Offshore seismic surveys, originally developed for finding oil and gas, can reveal buried river channels beneath the modern North Sea floor. They show landscapes covered by later marine sediments, valleys, floodplains, lake basins, and ancient surfaces that were once exposed to air. Sediment cores bring up pollen from long-vanished forests, peat from old wetlands, freshwater shells, and microscopic organisms that reveal whether a place was once a lake, a marsh, an estuary, or open sea. Fishing nets and dredging operations have recovered bones of mammoths, reindeer, bison, deer, and other animals from the seabed. They have also brought up worked flints, barbed points, fragments of tools, and other traces that people once moved through these drowned lands. None of this gives us a complete picture. The sea has eroded many sites. Rivers have cut through older deposits. Later sediments have buried others beneath meters of sand and mud. But enough survives to make one thing clear. Northern Europe did not simply lose a strip of coast after the Ice Age. It lost an inhabited landscape on a continental scale. And in the centre of that vanished world was a region that would become the most famous drowned landscape in Europe. A place we now call Doggerland. Doggerland. The name sounds ancient, like something carved into a Roman map or remembered in a medieval legend. But it isn't. It is a modern name borrowed from Doggerbank, the broad, shallow ridge beneath the central North Sea. Archaeologists and geologists use it as a convenient label for the lost lowlands that once connected Britain to continental Europe. And convenient is important, because Doggerland was not one kingdom. It was not one tribe. It was not one city with walls, temples, markets, and a single moment when it went under. It was a changing world spread across an enormous area, a mosaic of landscapes occupied and revisited by generations of hunter-gatherers as the climate warmed and the sea kept moving inland. At its greatest extent, this was a low country of river valleys, lake margins, marshes, open woodland, grassland, and coastal plains. Some parts were probably rich enough to support repeated seasonal camps. Others may have been travel corridors, hunting grounds, fishing places, or territories visited only at certain times of year. Imagine a family group moving through this world in spring. They follow a river channel where fish are running. They gather water birds' eggs from the marshes. They hunt deer at the woodland edge. They cut reeds, collect nuts and berries when the season allows, and shape flint tools beside a fire. They know which crossings become dangerous after rain. They know where herds gather. They know which low places flood when the tides are high. To them, this was not Doggerland. It was home, or perhaps several homes connected by memory, kinship, and roots, walked so often that they needed no map. And for thousands of years people adapted as that home changed. The rising ocean did not swallow the entire North Sea plain in one dramatic afternoon. In the earliest phases, water entered the lowest channels and basins. Rivers became wider, slower, and more tidal. Freshwater wetlands turned brackish. Salt-tolerant plants began appearing where reeds and sedges had once dominated. Forests retreated from drowned ground. New shorelines formed, then moved again. That process could be gradual on the scale of a lifetime, but not necessarily slow enough to ignore. A camp used by grandparents might be a salt marsh by the time grandchildren returned. A familiar river crossing could become an estuary. Hunting territory could be divided by water. The people who lived there did not need instruments to understand sea level rise. They could watch it happen in the changing behavior of tides, fish, birds, trees, and rivers. The evidence comes up from the seabed in fragments. Fishing boats have long hauled up bones from the North Sea, mammoth, woolly rhinoceros, reindeer, bison, elk, red deer, wild boar, and aurochs, the huge wild cattle that once ranged across Europe. Some belong to the coldest phases of the Ice Age. Others came from the warmer landscapes that followed. Together, they reveal just how radically this terrain changed before the sea finally covered it. Then there are the human traces. Worked flints have been recovered from dredged sediments and fishing grounds. Flint flakes, blades, points, and tools shaped by deliberate human hands. A piece of flint does not tell us the name of its maker or the story of a campfire conversation. But it tells us something undeniable. People were here. They hunted here, processed animals here, repaired tools here, and moved through a landscape that is now beneath waves. Peat layers offer an even more intimate record. Peat forms in waterlogged places where dead plant material accumulates faster than it decays. It is the compressed remains of old marshes, wet forests, and swampy ground. When researchers recover peat from beneath the North Sea, they can find pollen grains trapped inside it. Microscopic evidence of birch, pine, hazel, alder, grasses, and other plants that once grew on dry or damp land. Sometimes the remains are larger and more haunting. Tree stumps, roots, branches, entire ancient forest surfaces preserved beneath marine sediment. In a few places around the coasts of Britain, Wales, and the North Sea basin, low tides exposed drowned forests, dark stumps emerging from mud where waves now roll overhead. These are not necessarily the central heart of Doggerland itself, but they give us a glimpse of the kind of transformation happening across the wider region. Land became wetland, wetland became coast, coast became seafloor. Still, we should be careful about the picture this creates. Doggerland has become famous, partly because it invites a powerful fantasy, a prehistoric Atlantis beneath the North Sea, full of vanished villages waiting to be found intact. Reality is both less theatrical and, in some ways, more profound. There is no evidence for a lost city-state beneath the waves. No evidence of towers, palaces, armies, or an urban civilization, suddenly erased at 10,300 BC. Most of the people using this landscape were Mesolithic hunter-gatherers living in small mobile communities. Their settlements may have included temporary camps, more durable seasonal sites, hearths, shelters, processing areas and places, repeatedly used over generations. But small communities do not mean small losses. When a river mouth floods, people lose a fishing ground. When a wetland turns salty, they lose birds, reeds, fresh water and grazing habitat. When the sea cuts through a low ridge, a route to neighbouring groups may become a dangerous crossing or disappear entirely. A landscape can be culturally dense even without cities. Every hill, inlet, camp, burial place and hunting route can carry meaning. And as the waters rose, Doggerland became more fragmented. What had once been a broad, connected plain narrowed into peninsulas, islands, estuaries and tidal wetlands. Britain gradually became less a western extension of Europe, and more a land separated by water. The exact sequence varied from region to region, because local land movement, sediment, tides and river systems all mattered. But the long-term direction was unmistakable. The world was breaking apart. Then, thousands of years after the period around 10,300 BC, another disaster struck the remaining lowlands. Around 6,200 BC, off the coast of Norway, a huge mass of seafloor sediment collapsed in what is called the Storegga Slide. The collapse generated a tsunami that raced across the Norwegian Sea and into the North Sea. Geological deposits in Scotland, Norway, the Shetland Islands, and elsewhere show that the waves reached coasts with devastating force. Could the Storegga tsunami have hit the last remnants of Doggerland? Very likely. Some reconstructions suggest that the remaining low-lying areas, already reduced by millennia of sea level rise, were especially vulnerable. But this was not the event that drowned Doggerland from a vast plain beneath a single wave. The slow drowning came first. It took thousands of years. The tsunami was a later catastrophe, striking a landscape that had already been cut down to fragments. And maybe that is why Doggerland has such a hold on the imagination. It is not just a lost place. It is proof that maps are temporary. The North Sea feels permanent because we were born with it. But for most of human existence in northern Europe, that sea was different, smaller, farther away, or absent from places where people walked, hunted, and built lives. Doggerland reminds us that prehistory is not empty time. It was filled with human worlds with names we will never know, stories we can no longer hear, and coastlines now buried beneath one of Europe's busiest seas. And Europe was not the only place where rising water was remaking entire human landscapes. Far to the south, another sea basin may hold one of the most debated flood stories of all, and Europe was not the only place where rising water was remaking entire human landscapes. Far to the south, another sea basin may hold one of the most debated flood stories of all, the Mediterranean. Today it feels ancient and permanent, a blue world ringed by Europe, Africa, and the Near East. A sea of islands, harbours, olive groves, cliffs and cities so old that some of their names have survived for thousands of years. But at the end of the Ice Age, its coastlines were somewhere else. When global sea levels were lower, the Mediterranean was smaller. Not gone, because it remained connected to the Atlantic through the Strait of Gibraltar, but pulled back from many of the coastal plains we know today. River valleys extended farther out, broad lowlands existed at the mouths of rivers. The Adriatic, for example, was much reduced. Large areas of what is now shallow seabed were dry land, crossed by rivers draining the Alps and the Balkans. The northern Adriatic was not always a sea separating Italy from the Balkans. During lower sea levels, it was a broad plain, a place where rivers joined, wetlands spread, animals moved, and people could travel across landscapes now covered by water. The same thing happened around the Aegean islands that are separated today, may have been larger, closer together, or connected by exposed shelves and narrow land bridges. The coast of western Anatolia extended outward. The mouths of the Nile, the Rhone, the Po, and countless smaller rivers lay far beyond their modern positions. And as the ice sheets melted, all of that began changing, not in one identical wave across every coast. The Mediterranean is too complicated for that. It has narrow straits, deep basins, mountain-backed shorelines, sinking deltas, rising tectonic blocks, and rivers constantly building new land even as the ocean takes it away. In some places, the sea advanced quickly across flat ground. In others, steep terrain meant the shoreline moved only a short distance inland. A metre of sea level rise can drown an enormous area on a shallow plain and almost nothing along a cliff. But the direction was clear. Water was moving inland. Estuaries formed where river valleys had been. Salt water pushed into freshwater marshes. Coastal lakes became lagoons. Fishing grounds, campsites, crossing routes and river-mouth settlements had to be abandoned, moved or adapted. And then there is the Black Sea. This is where the story becomes controversial. The Black Sea is connected to the Mediterranean through a chain of narrow waterways, the Bosporus, the Sea of Marmara, and the Dardanelles. Today, seawater flows through this system, and the Black Sea is a vast brackish inland sea bordered by modern Turkey, Bulgaria, Romania, Ukraine, Russia, and Georgia. But during the last ice age, when global sea level was far lower, that connection may not always have functioned the way it does now. In the 1990s, geologists William Ryan and Walter Pittman proposed a dramatic idea. They argued that the Black Sea had once been a much smaller freshwater lake, isolated behind the Bosporus sill. Then, as post-glacial sea level rose in the Mediterranean, water eventually overtopped that barrier. According to the strongest version of their hypothesis, the breakthrough was catastrophic. Mediterranean water rushed through the Bosporus like a giant waterfall, carving and widening the channel, then pouring into the lower Black Sea basin. Shorelines advanced rapidly across former lowlands. Perhaps tens of thousands of square kilometres were flooded over a relatively short time. Picture people living near a freshwater shore. They fish in rivers, gather reeds from marshes, hunt along forest edges, and travel between settlements across open lowlands. Then the water begins arriving from the south. At first, maybe it is distant. A change in currents, a taste of salt, a shoreline that no longer behaves the way it used to. Then the old landscape starts disappearing. It is an extraordinary scenario, and it immediately captured the public imagination. Some people connected it to ancient flood traditions. Could this have been the origin of the biblical story of Noah? Could refugees from the expanding Black Sea have carried memories of disaster into early farming communities of the Near East? Could one regional inundation have become, over generations of storytelling, a flood that covered the entire world? It is possible to see why the idea spread, but compelling is not the same as proven. The Black Sea flood hypothesis rests on real evidence. Researchers have found submerged former shorelines beneath the modern sea. Sediment cores show changes from freshwater conditions to more marine conditions. Fossil shells can reveal whether a layer formed in a lake, a brackish sea, or a marine environment. Sonar surveys have identified drowned landscapes, channels, and surfaces that were once exposed or close to the surface. These clues show that the basin changed dramatically as sea levels rose after the Ice Age. What they do not yet prove, at least not to everyone's satisfaction, is one single sudden flood of the scale first proposed. Other researchers argue that the connection between the Mediterranean and Black Sea may have opened earlier, developed more gradually, or involved repeated shifts in water exchange, rather than one apocalyptic breach. Some reconstructions suggest the Black Sea was not a simple freshwater lake waiting behind a dry barrier. It may already have been brackish. Its water level may have fluctuated. The timing of shoreline changes, shell deposits and sediment transitions remains difficult to pin down precisely. And timing matters. The most famous catastrophic flood version is generally placed around 5600 BC, thousands of years after 10,300 BC. That means it cannot simply be treated as direct evidence for the meltwater pulse we are investigating. It belongs to the larger story of post-glacial sea level rise, but it may represent a regional threshold event. Mediterranean water entering a partly enclosed basin after a particular local barrier was crossed. That is very different from saying the whole planet experienced an overnight flood. Global meltwater raises the ocean, but each coast responds in its own way. A rising Mediterranean may push through the Bosporus only when local water levels, channel depth, basin elevation and erosion line up. The global signal provides the pressure. The geography determines the drama. Still, the archaeological potential is enormous. Around enclosed seas, old shorelines can be buried beneath layers of sediment, rather than destroyed by powerful open ocean waves. Submerged caves may preserve evidence of changing water levels. Drowned river valleys can contain ancient soils, wood, pollen, animal remains, and perhaps human artifacts. Underwater surveys around the Black Sea, the Aegean and the Adriatic have already found ancient coastal features and later shipwrecks preserved in remarkable conditions. But finding a prehistoric settlement is another matter entirely. The people living around these shores were not building stone cities that would survive neatly on the seabed. Many lived in small settlements of wood, reed, mud and earth. Rising water, erosion, sediment movement, and later human activity may have scattered or buried almost everything. So yes, there may be lost landscapes beneath the Mediterranean and Black Sea. There may be drowned camps, villages, graves and paths that people once walked. But we should resist the temptation to turn every submerged shoreline into Atlantis and every sediment layer into Noah's flood. The data tells us something real. The sea transformed human worlds. The stories we attach to that transformation are where certainty begins to fade. And if the Black Sea may preserve the outline of a drowned inland world, Southeast Asia preserves something even larger. A lost subcontinent of lowlands. Today, look at a map of Indonesia, Malaysia, Brunei, Singapore and southern Thailand, and you see a shattered geography. Peninsulas, straits, thousands of islands, Sumatra on one side of the Malacca Strait, Java farther south, Borneo looming to the east, water everywhere. But during the last ice age, much of that water was land. This drowned landscape is called Sundaland, and at the height of lower sea levels, it connected mainland Southeast Asia with Sumatra, Java, Borneo, and many smaller islands that are now separated by shallow seas. The South China Sea was smaller. The Java Sea was mostly dry land. The Gulf of Thailand was not a gulf in the modern sense. It was part of a broad, low-lying continental shelf stretching south and east from the Asian mainland. You could have walked from what is now Thailand into the Malay Peninsula, then onward across open country towards Sumatra or Borneo. Not across one smooth, empty plain. Sundaland was enormous, varied and alive. It contained hills, forests, swamps, lakes, river valleys, floodplains and coastal wetlands extending far beyond today's shorelines. For people living there, this was not a collection of islands at all. It was a world, and it was one of the most important human landscapes on Earth. Modern humans had reached Southeast Asia tens of thousands of years before the final flooding of Sundaland. They had moved through a region that offered rich resources: fish, shellfish, freshwater animals, tropical plants, birds, forests full of game, and rivers that acted like highways through difficult terrain. Some of the largest rivers in the region did not end where they do today. When sea level was lower, rivers now separated by ocean may have joined across the exposed shelf. Researchers have reconstructed possible giant drainage systems flowing through the lowlands, carrying water from what are now the Malay Peninsula, Sumatra and Borneo toward the sea. The exact shape of those ancient rivers is still debated. Sediment, shifting channels, and later flooding have made the evidence difficult to read. But the basic picture is clear enough. Where there is now shallow ocean, there were once river valleys. And where there are river valleys, there are usually people. Think about what a drowned river mouth offers. Fresh water, fish, shellfish, migrating animals, edible plants, flat ground for camps, easy travel by canoe or on foot. A place where different groups can meet, exchange tools, find partners, share information, and pass stories from one generation to the next. These were exactly the kinds of landscapes early populations would have favoured. Then the water started coming back. As the great ice sheets melted, the ocean crossed the edge of the Sunda shelf and began moving inland. At first the changes may have seemed local, a tidal channel reaching farther upriver, salt water killing freshwater plants in a marsh, a lagoon forming where a meadow used to be, a familiar crossing route becoming dangerous at high tide. But on a shelf, this flat, small changes in sea level could produce huge changes on the map. A coastline does not need to rise like a wall to transform lives. It only needs to advance far enough to cut a river valley, isolate a hunting ground, drown a freshwater source, or turn a day's walk into a sea crossing. Over thousands of years, Sundaland fragmented. The lowlands between Sumatra and the mainland disappeared beneath the Malacca Strait. Water spread across the basin that became the Java Sea. Borneo separated from Java, Java separated from the mainland. Forests and river systems that had once formed connected landscapes were divided into islands. The geography of modern Southeast Asia was being born, and for human populations, that meant adaptation or movement. Some groups may have retreated toward higher ground as the coastal plain narrowed. Some may have followed rivers inland, others may have moved along the newly changing coastlines, taking advantage of estuaries and marine food. And some may have crossed increasing stretches of water, developing or improving the boat-building skills needed to survive in an island world. This matters because Southeast Asia was never simply a dead end on the path of human migration. Beyond Sundaland lay Wallacea, the zone of deep-water islands between Asia and Sahul, the ancient continent formed by Australia and New Guinea. Even when sea level was at its lowest, deep channels remained between parts of Sundaland and Wallacea. Getting farther east required water crossings. So, as Sundaland flooded, routes were not merely erased. New maritime routes may have become more important. People who understood tides, currents, coastlines and boats would have had an advantage. The rising sea was a disaster in some places, but it was also a force pushing human societies toward new forms of mobility. And this is where the mystery gets frustrating. If you enjoy these kinds of unresolved ancient mysteries, the channel's book on 12 Unexplained Mysteries goes much deeper into the evidence, the debates and the questions nobody has fully answered. You can find it on the website through the link in the description. Because Sundaland should be one of the richest archaeological regions on the planet. It was vast, it was habitable, it stood directly along major routes of human movement. It contained the river mouths and wetlands where people often gathered. But most of it is underwater, and tropical shelf archaeology is brutally difficult. Warm water, powerful currents, sediment movement, coral growth, storms, and rising seas can destroy or bury ancient surfaces. Organic materials decay rapidly. Wooden structures vanish. Small stone tools can be scattered across kilometres of seabed or hidden under thick layers of mud. Visibility underwater can be poor. Surveying an area the size of a subcontinent is expensive, slow, and technically demanding. The absence of discovered villages does not mean nobody lived there. It may mean we have barely begun looking. Researchers are increasingly using sonar, sediment cores, underwater mapping, and ancient environmental DNA to identify buried river channels, old soils, peat deposits, and former shorelines. These are the first steps toward locating places where human traces might still survive. And if settlements are eventually found, they may change how we understand the peopling of Southeast Asia and Australia. They may also tell us something about flood memories. Southeast Asia and the wider Pacific contain many traditions involving drowned lands, overwhelming waters, islands changing shape, and people escaping by boat or seeking higher ground. It is tempting to treat these stories as direct memories of ice age, sea level rise. We cannot do that. Oral traditions change. They merge with local storms, tsunamis, river floods, volcanic eruptions, and later migrations. A story written down recently may contain layers from many different events. There is no simple line from a modern flood legend back to one shoreline crossing 10,000 years ago. But the possibility is not absurd either. For generations living on a retreating coast, the sea would have been a constant presence. It would have taken places with names, fishing grounds, burial sites, camps, forests, entire routes across country their grandparents may have known. Not overnight in the literal sense, not all at once across the whole region, but fast enough in the memory of communities to make the ocean seem alive, hungry, and unstoppable. And beyond those newly broken islands, another enormous landmass was facing the same transformation. Sahul, the world of the first Australians. Beyond those newly broken islands lay Sahul, not Australia as we know it, not New Guinea as we know it, not Tasmania, separated by the cold waters of Bass Strait. Sahul was one enormous continent. When sea levels were more than 100 metres lower than today, Australia, New Guinea and Tasmania were joined by exposed land. The Torres Strait, which now separates northern Australia from New Guinea, was dry country. The Arafura Sea was a broad lowland, and Bass Strait between mainland Australia and Tasmania was a landscape of grasslands, rivers, lakes and rolling ground where people and animals could move between regions that are now divided by ocean. For the first Australians, this was not an island continent at the edge of the world. It was a vast connected homeland stretching from tropical New Guinea to the temperate south, and people had been living in it for a very long time. Modern humans reached Sahul at least 50,000 years ago, and possibly much earlier. Getting there already required extraordinary journeys. Even at the lowest sea levels, the deep water islands of Wallacea stood between Sundaland and Sahul. There was no continuous land bridge from Asia into Australia. Someone had to build watercraft. Someone had to organise a group. Someone had to look across a horizon of open water and decide that land existed beyond it. That was one of the greatest migrations in human history. But once people reached Sahul, the coastline they knew did not stay still. As the ice sheets melted, water began advancing across the continent's low margins. The changes were not identical everywhere. In some places, cliffs held the sea back. In others, especially across broad, shallow shelves, the coastline could travel astonishing distances inland. Northern Sahul changed dramatically. The lowlands between Australia and New Guinea were slowly drowned as the Arafura Sea expanded. Rivers, wetlands, hunting grounds and travel routes vanished beneath salt water. What had once been a land connection narrowed, broke into channels, and eventually became the Torres Strait. That separation was not just a line appearing on a map. It divided communities that had once been part of the same continental world. To the south, Bass Strait formed as the sea flooded the low plain between Tasmania and mainland Australia. Tasmania became an island. People who remained there became increasingly separated from communities on the mainland, with the crossing eventually becoming too wide and dangerous for routine contact. Imagine what that meant across generations. A family's old travel route is gone. A place where people once gathered seasonally is now a tidal channel. Freshwater wetlands become salty bays. Hills that once stood inland become islands. The coastline keeps moving, and every move forces a decision. Retreat inland, shift to different foods, learn new boat routes, or leave. This is why Submerged Sahul matters so much. The earliest people in Australia and New Guinea were not living only in caves, rock shelters, and inland deserts. Many must have lived along coasts, estuaries, river mouths, and shallow water wetlands. Those places would have offered fish, shellfish, birds, turtles, plant foods, fresh water, and easy routes of movement. But the coast they used is now underwater. The oldest shoreline camps may lie far beyond modern beaches, buried beneath sediment in the Arafura Sea, the Gulf of Carpentaria, the Great Barrier Reef Shelf, and Bass Strait. Archaeologists have found important evidence of ancient life along today's coasts. But today's coast is not the coast where the first generations of Sahul lived. That is the problem. We are looking for some of humanity's earliest maritime lifeways in places the sea has spent 10,000 years reshaping. Still, the search is beginning. Underwater surveys, sediment cores, sonar mapping, and studies of ancient river channels are revealing landscapes that once stood above water. In some areas, researchers have identified drowned freshwater systems, old lake beds, and land surfaces with the potential to preserve evidence of human activity. Potential is not proof. A mapped river valley is not a discovered village. And a submerged plain does not automatically mean a lost city. But it tells us where people could have lived and where the archaeology of their lives may still be waiting. Then there are the stories. Across Aboriginal Australia, Indigenous communities hold deep knowledge of country, coastlines, water, animals, and places transformed by the sea. Some oral traditions describe land lost to rising water, coastal routes disappearing, and islands separating from the mainland. A few researchers have suggested that certain stories may preserve memories of post-Ice Age sea level rise, perhaps passed down over thousands of years. That possibility is remarkable, but it requires care. Oral traditions are not frozen recordings from the distant past. They are living knowledge systems. Stories can preserve environmental observations across immense spans of time, but they can also carry many layers: local floods, cyclones, storm surges, tsunamis, social change, spiritual meaning, and events beyond what geology can date precisely. We should not force every story into a geological timeline, and we should not treat Indigenous knowledge as a puzzle piece that only matters when it appears to confirm Western science. But neither should we dismiss it. For people whose ancestors watched the sea take familiar ground, changing water would not have been an abstract global average measured in millimeters per year. It would have been personal, a fishing place gone, a route cut off, a named landscape transformed, and Sahul adds one more complication to the Meltwater story. Global sea level is not local sea level. The ocean may rise worldwide, but each coast experiences that rise differently. Land can sink or rebound. Tectonic forces can lift one shoreline while another subsides. Currents, tides, sediment, and the shifting gravitational pull of melting ice sheets can all alter the regional pattern. So there was no single moment when all of Sahul flooded, in exactly the same way. There were many coastlines, many local disasters, many adaptations. And as Australia, New Guinea and Tasmania became separate worlds, another drowned shelf may have become a refuge instead of a barrier, the low basin now hidden beneath the Persian Gulf. And as Australia, New Guinea and Tasmania became separate worlds, another drowned shelf may have become a refuge instead of a barrier, the low basin now hidden beneath the Persian Gulf. Today, the Persian Gulf is a long, shallow arm of the Indian Ocean, squeezed between Arabia and Iran. At its deepest, it is not very deep by ocean standards. Much of its floor lies beneath less than 100 meters of water. During the Ice Age, when sea level was far lower, that floor was dry land. Not a featureless desert, necessarily. A vast low basin crossed by rivers. The Tigris and Euphrates, which now meet near the northern end of the Gulf, would have flowed much farther south. Other rivers came down from the Iranian plateau. Seasonal waterways crossed eastern Arabia. Together, they may have formed a huge river system draining through what is now the Strait of Hormuz into the Arabian Sea. This is the Persian Gulf Oasis hypothesis. The basic idea is straightforward. While much of Arabia was dry, the exposed Gulf basin may have held freshwater rivers, marshes, lakes, floodplains and wetlands. A landscape capable of supporting plants, animals and human communities. And if that is true, it matters enormously. Look at a modern map. Southwest Asia is a crossroads. Africa lies to the west. The Iranian plateau and Central Asia lie to the north and east. Mesopotamia opens toward the Levant. Arabia stretches south toward the Indian Ocean. For people moving across this region during the late Ice Age, water was everything. A fertile basin in the middle of this dry zone could have been a refuge. A place where groups survived difficult climatic periods. A meeting ground where populations from Arabia, Mesopotamia and Iran encountered one another. Perhaps even a corridor linking migrations that would otherwise seem separated by deserts and mountains. Think of it as a hidden heartland. Not hidden then, of course. It would have been visible, lived in, travelled through, but hidden now beneath the Gulf. Some researchers have proposed that the basin was especially important when surrounding parts of Arabia became more arid. As lakes dried up and grasslands retreated, people may have concentrated around dependable rivers and wetlands in the Gulf lowlands. Small communities could have hunted gazelle, gathered plants, fished river channels, and moved seasonally through a rich patchwork of habitats. That is plausible, but plausible is not the same as proven. This is where the mystery gets frustrating. The best place to search for evidence is underwater, and underwater archaeology in the Persian Gulf is extremely difficult. The water is shallow in many places, but shallow does not mean easy. Tides are strong, sediment moves, modern shipping, dredging, oil development, and coastal construction have disturbed parts of the seafloor. Ancient landscapes may be buried beneath meters of mud or erased by waves as the rising sea crossed them. So far, no one has found a buried Ice Age city beneath the Gulf. No stone streets, no temples, no palace walls, no lost civilization with writing pyramids or impossible technology. Those claims go far beyond the evidence. The Oasis hypothesis does not require cities. In fact, it would be surprising to find them there at 10,300 BC. This was thousands of years before the first known cities emerged in Mesopotamia. What archaeologists would expect if people lived in the basin are campsites, hearths, stone tools, fish bones, animal remains, shell deposits, and traces of structures made from wood, reeds, or mud. Exactly the kinds of evidence least likely to survive repeated flooding. There are clues around the edges. Along the shores of the modern Gulf, archaeologists have found early Holocene settlements, including communities associated with the Ubaid period several thousand years later. Some of these sites appear remarkably early and widespread along a coastline that was still changing. They show that people were living around the Gulf as the waters advanced. But they do not prove that their ancestors came from a drowned oasis in the basin. They could have arrived from Mesopotamia, Iran, Arabia, or multiple directions. The archaeological record is incomplete, and the missing centre of the map makes every explanation harder to test. Still, the geography is difficult to ignore. As sea level rose after the last ice age, seawater entered through the Strait of Hormuz and moved northwestward into the low basin. The shoreline would not have advanced as a neat, steady line. Tides pushed inland, river mouths shifted, marshes became estuaries. Fresh water channels turned brackish, then salty. Low ground disappeared, while ridges and higher patches became temporary islands. For communities living there, the transformation may have unfolded across generations. But in the flattest parts of the basin, a relatively modest rise in water level could move the shoreline many kilometres. A hunting route becomes a marsh. A wetland becomes an inlet. A familiar river becomes tidal water, and the human routes across Southwest Asia changed with it. When the Gulf Basin was exposed, people may have crossed its lowlands on foot, following rivers between Arabia and southern Mesopotamia. As the water rose, those routes narrowed and broke apart. Movement increasingly had to go around the growing Gulf, through northern Mesopotamia along the Iranian coast, or across Arabia's harsher interior. The sea did not simply erase land, it reorganized the map of human contact. And somewhere beneath the modern Gulf, beneath shipping lanes and oil fields and shifting sediments, may lie the remains of landscapes where people adapted to that change in real time. But the Persian Gulf was only one drowned corridor in a much larger world. Follow the coastline south from Arabia, around the Horn of Africa, down the shores of East Africa, and across the Indian Ocean toward India and Southeast Asia, and you are following one of the most important possible migration routes in human history. Today, much of that route is underwater. During the last ice age, when sea level was more than 100 meters lower than it is now, the continental shelves around Africa and the Indian Ocean were wider. In some places dramatically wider, land extended beyond the modern shore. River valleys continued across plains that are now seabed. Bays were smaller, islands were larger, and narrow water crossings may have looked very different. For people living along these coasts, the edge of the world was not where it is today. That matters because many researchers think coastal environments played a major role in the spread of Homo sapiens beyond Africa. The exact route remains debated. Some groups may have moved through the Nile Valley and the Levant. Others may have crossed from the Horn of Africa into southern Arabia, then followed coastlines eastward. This is often called the Southern Coastal Migration Model. The model is not a claim that one single band of people marched along one unbroken beach, leaving Africa and reaching Australia in a few generations. Human movement never works that neatly. Populations pause. They split, they turn inland, they disappear, they mix with other groups. They adapt to local conditions, but coastlines offer something incredibly valuable to small mobile communities. Food, shellfish, crabs, fish trapped in tidal pools, seabirds and their eggs, mangroves, edible plants, fresh water where rivers meet the sea, large animals drawn to wetlands. And perhaps most importantly, shorelines provide a route that is easier to navigate than an unfamiliar interior. Keep the water on one side. Follow the bays, estuaries, and river mouths. Move when resources decline. Camp where fresh water and food overlap. A coast can be a highway, except the Ice Age highway is now beneath the ocean. Take the Red Sea. Today it separates northeast Africa from Arabia. At its southern end lies the Bab el-Mandeb, the Gate of Tears, a narrow strait between the Horn of Africa and Yemen. Modern maps make it look like a relatively small crossing, but during periods of low sea level, the geography changed. The strait narrowed islands and exposed shelves altered the route, and the distance of open water may have been reduced. Reduced does not mean eliminated. There was still water to cross. And whether early humans had boats capable of making that crossing at particular times remains a major question. But the possibility matters. If people could cross there, even using simple rafts, floats, or short island-to-island journeys, Arabia opened before them. From there they could follow the shores of the Arabian Sea toward Oman, Pakistan, and India. Now imagine what happened as the ice sheets melted. The Red Sea rose, coastal plains drowned, estuaries shifted inland. Springs close to the old shore may have been swallowed by salt water. Groups who had lived near productive tidal flats found themselves pushed toward higher ground, or forced to move along a coastline that kept changing beneath their feet. And this was not just a story of rising water. The climate itself was changing. Across Africa and the Indian Ocean world, monsoon systems shifted repeatedly as the planet warmed. Rain belts moved, seasonal winds strengthened or weakened. Rivers that had once carried dependable water could become erratic. Dry valleys could flow again during wet phases. Lakes expanded, then contracted. Grasslands advanced into regions that later became desert. The coast was never an isolated strip of sand, it was connected to everything inland. A stronger monsoon meant more water flowing down rivers toward the sea, that could create fertile estuaries, wetlands rich in fish and birds, and broad floodplains attractive to humans and animals alike. But it could also mean floods, unstable channels, and sediment burying old campsites beneath layers of mud. A weaker monsoon could shrink rivers and stress inland populations. In those periods, the coast may have become even more important, offering marine food when the land failed. This is especially relevant along East Africa. The modern coast of Kenya, Tanzania, Mozambique, and Somalia conceals a much broader prehistoric landscape offshore. When sea level was lower, people could have lived far beyond the present shoreline, near ancient river mouths or lagoons that no longer exist. The same is true around the Horn of Africa, along the Arabian coast, and across parts of the western Indian Ocean. But finding evidence is another matter entirely. Underwater archaeology is not equally developed everywhere. The North Sea has received decades of intensive study because of offshore construction, fishing, energy projects, and research funding. Parts of the Mediterranean have been surveyed in great detail. By comparison, enormous stretches of the African and Indian Ocean shelves remain poorly mapped for prehistoric archaeology. Some areas are politically difficult to access. Others are remote, deep, or affected by strong currents and poor visibility. In tropical waters, coral growth, storms, sediment movement, and biological activity can damage or hide ancient surfaces. Along heavily populated coasts, ports, dredging, trawling, and modern development may have disturbed the seabed before anyone had a chance to investigate it. And even if an ancient campsite survived, it may not look impressive. No city walls, no giant monuments, maybe a scatter of stone flakes buried beneath sand. A hearth layer covered by marine sediment, fish bones that dissolved long ago in acidic soils, post holes from wooden shelters, impossible to recognize after thousands of years underwater. The evidence we would most want is often the evidence least likely to survive. That creates a dangerous misunderstanding. People look at the map, see few submerged sites reported from East Africa or the Arabian Sea, and conclude that no one lived there. But absence of discovered sites is not proof of absent people. Sometimes it means nobody has looked. Sometimes it means the right survey equipment has not been used. Sometimes it means the old shoreline lies beneath sediment, beyond the reach of divers or underwaters too difficult and expensive to explore. And sometimes, yes, it may mean a particular area was not occupied. The point is that archaeology has to distinguish between those possibilities. There are hints, though not final answers. Coastal shell middens, fishing evidence, and early settlements on surviving shorelines show that ancient people in Africa, Arabia, India, and island Southeast Asia were capable of using marine environments. Genetic patterns also suggest that humans spread rapidly through southern Asia and eventually into Sahul. That expansion had to pass through a world of coasts, islands, rivers, and changing seas. The drowned shelves may hold parts of that story, not necessarily lost cities. Something more fundamental. The camps of people who learned that the ocean was not an ending, but a source of food, a route of travel, and eventually a bridge between continents. And that brings us to the central problem. If the drowned shelves hold parts of the human story, why haven't we found them? Why aren't museums full of 12,000-year-old coastal villages lifted from the bottom of the North Sea, the Persian Gulf, the Red Sea, or the Sunda Shelf? Because the seabed is not a time capsule. It is an active, destructive, constantly changing environment. And the moment a settlement is flooded, it enters a world that can erase it in a dozen different ways. Start with the rising water itself. As the shoreline moved inland, waves attacked the old coast. Storms tore into dunes, beaches, riverbanks, and low-lying campsites. Tides carried sediment away. Currents scoured exposed surfaces. A place where people had lived for generations could be broken apart in a matter of decades. Its artifacts scattered across the seabed, its structures reduced to fragments, its original location impossible to recognize. Then there is erosion on a larger scale. When sea level rises over a continental shelf, it does not simply cover the old landscape with a neat blanket of water. It reshapes it. Ancient river valleys can become tidal channels. Old hills can become islands, then reefs, then vanish beneath shifting sand. Sediment moves back and forth with tides and storms, sometimes exposing an ancient surface for a few years, then burying it beneath meters of mud. And burial is both good news and bad news. Bad news, because a site hidden under thick sediment cannot be seen by divers or ordinary seabed surveys. Good news, because if sediment covered a campsite quickly enough, it may have protected it from waves, oxygen, scavengers, and later disturbance. Some of the best preserved submerged landscapes are not the ones lying exposed on the seafloor. They are the ones entombed beneath layers of sand, clay, peat, or river mud. The problem is getting to them. Imagine trying to find a campfire from 10,000 years ago. Not on an open field, not even at the bottom of a clear lake, but beneath 20 meters of seawater below a busy shipping route, under several meters of sediment, on a landscape that no longer resembles the one where people lived. That is the challenge. And the things most likely to tell us about ordinary coastal life are often the first things to disappear. Stone tools can survive. Flint flakes, axe heads, grinding stones, hearthstones, and sometimes the foundations of more substantial structures can last for thousands of years. In rare conditions, archaeologists may find wooden fish traps, preserved footprints, animal bones, or even plant remains. But most prehistoric coastal settlements were not built from stone. Homes may have been made from wood, reeds, hides, grass, bark, branches, and packed earth. Boats may have been hollowed logs, stitched planks, bundled reeds, or skin-covered frames. Nets, baskets, ropes, clothing, mats, food stores, and wooden tools were all essential to life. Yet these are perishable materials. They rot, they are eaten by marine organisms, They are broken down by bacteria. They dissolve, drift away, or leave behind traces so faint that even experienced archaeologists can miss them. A stone blade tells you that someone was there. A lost net, a wooden paddle, a basket of shellfish, or a shelter made from reeds might tell you how they lived. Those are the things the sea is especially good at destroying. Human activity makes it worse. For thousands of years, fishing boats have dragged heavy trawl gear across parts of the continental shelf. Modern dredging removes sediment for construction. Ports expand, pipelines are laid, wind farms are built. Sand and gravel are extracted. Anchors, cables, drilling, shipping, and coastal engineering all disturb the seabed. Sometimes development reveals archaeology. A survey for an offshore wind farm may detect an ancient river channel or a buried peat bed that nobody knew existed. But development can also damage a site before its significance is understood. So how do archaeologists search for something they cannot see? They do not begin by hunting for houses. They begin by hunting for land. That sounds obvious, but it is the key to everything. Before looking for human traces, researchers have to reconstruct the drowned landscape itself. Where were the rivers? Where were the freshwater springs? Where were the marshes, lake edges, sheltered bays, ridges, and old coastlines? Which areas would have been dry land at the time people could have lived there? Because people did not settle randomly across the landscape. They tended to choose places with fresh water, food, shelter, good visibility, access to travel routes, and raw materials. Find the ancient river valley, find a former lake shore, find a peat-filled wetland beside a protected inlet. Now you have somewhere worth searching. This is where the technology becomes extraordinary. Side-scan sonar sends sound across the seabed and maps its texture. It can reveal channels, ridges, wrecks, stone features and patterns that do not belong to the natural seafloor. Multi-beam sonar creates detailed maps of underwater topography, showing drowned valleys and former hills in remarkable detail. But sonar mostly sees the surface. To look beneath it, archaeologists use sub-bottom profiling. This sends acoustic signals down through sediment and records the echoes from buried layers. In effect, it allows researchers to see a cross-section of the seabed. Modern sand on top, then older marine mud, then perhaps a layer of peat formed in a freshwater marsh before the sea arrived. That peat layer can be a jackpot. It tells archaeologists they may have found an ancient land surface. And if people lived nearby, there could be tools, hearths, worked wood, animal bones, pollen, seeds, or microscopic traces of human activity preserved within it. Sediment cores are how they test that possibility. A long tube is driven into the seabed and pulled back up, bringing with it a vertical sample of thousands of years of environmental history. Researchers can examine the layers, identify pollen from ancient plants, fragments of charcoal from fires, shells from changing environments, and chemical clues about whether a place was freshwater, brackish, or marine. Then comes dating. Radiocarbon dating can establish when peat formed, when wood was cut, or when a shellfish died. Other methods can date sediments or track shifts in sea level. Without that chronology, an object on the seabed is just an object. A stone tool might have been dropped from a boat last century. A piece of wood may have washed in from somewhere else. Context is what turns a find into evidence. That is why spectacular claims require spectacular care. A sonar image that looks like a wall is not automatically a lost city. It may be a natural rock ridge, a modern pipeline trench, a fishing scar, or an illusion created by the angle of the survey. A group of stones may be a structure, or they may be stones, to claim a drowned settlement. Archaeologists need the full chain, a securely identified ancient land surface, human-made artifacts in their original geological context, reliable dates, evidence that the objects belong together. Preferably multiple lines of support, tools, hearths, food remains, post holes, environmental data, and a landscape where a settlement actually makes sense. That standard can feel frustratingly cautious, but it is what separates discovery from wishful thinking. The drowned world is real, the lost coastlines are real. People almost certainly lived on many of them, but the sea has had thousands of years to scatter, bury, dissolve and disguise the evidence. Which means the question is not simply, where are the lost cities? It is more difficult than that. What kinds of human lives can survive the ocean long enough for us to find them at all? And that question leads directly to the word that appears in almost every dramatic version of this story. Cities. Did cities vanish when the sea rose? The honest answer is, probably not cities in the way most people imagine them. When we hear the word city, we picture streets, stone buildings, markets, walls, temples, harbours, governments, maybe thousands or tens of thousands of people living close together. We picture somewhere like Memphis, Athens or Rome, a place with monuments big enough to leave ruins behind. But 10,300 BC was long before the first historically recognized cities. Agriculture was only beginning to emerge in a few regions. Writing did not exist. States did not exist. Kings, taxes, bureaucracies, city walls and monumental urban centres were still thousands of years in the future. That doesn't mean the coasts were empty. Far from it. It means we need better words. Some places were camps. A few families stopping beside a river, a beach or a shellfish bed for days, weeks, maybe a season. They left hearths, stone flakes, broken tools, bones, shells, and little else. Some were seasonal gathering places, locations where scattered groups came together when fish ran, birds migrated, nuts ripened, or large animals crossed a particular route. For part of the year, these places may have been crowded, noisy, busy, full of trade, marriage alliances, feasting, ritual, storytelling, and exchange. Then the season changed, and the population dispersed again. Some were villages, more permanent settlements where people returned year after year, perhaps living in huts or substantial wooden structures, managing local resources, storing food, burying their dead, and maintaining social ties with communities many miles away. And some may have been complex settlements unlike anything we have yet found beneath the sea. That possibility matters. Human beings had already been living along coasts, rivers, lakes, and wetlands for an incredibly long time. They understood seasonal cycles. They knew how to fish, gather shellfish, hunt waterfowl, travel by boat, preserve food, shape wood, weave fibres, and move goods across large distances. A productive estuary could support far more people than an inland hunting camp. A sheltered bay with fresh water nearby. Fish in the shallows, birds in the marshes, and forests on higher ground could become a place people returned to for generations. Maybe centuries. So could there have been population centres on drowned coastlines that we have not discovered? Absolutely. But population centre is not automatically city. Picture a large coastal village on land that is now 30 metres below the North Sea. Not a marble metropolis. No pyramids. No paved roads. But perhaps dozens of homes built from timber, reeds and hide. Canoes pulled above the tide line. Fish traps in the shallows. Smoke rising from hearths. Children growing up in one place instead of constantly moving. People arriving from neighbouring groups to exchange stone, amber, shells, animal skins, stories, and marriage partners. That would have been a major settlement by the standards of its time. And if the coastline moved inland, That settlement could disappear so completely that nobody today even knows its name, its location, or whether it ever existed. This is the point that often gets lost. You do not need a lost global civilization to explain why the archaeological record has gaps. You only need geography. During the last ice age, sea level was much lower. Huge areas of continental shelf were dry land. These were not tiny strips of beach. In some places they were vast plains, river valleys, wetlands, forests, grasslands, and connected lowlands larger than modern countries. Then the ice melted. As the shoreline advanced, people did what people always do when conditions change. Some moved inland, some shifted to higher ground, some followed rivers. Some abandoned familiar places. Some may have tried to stay until storms, saltwater, erosion, or failing freshwater supplies made life impossible. The land did not vanish in one magical night, but over generations and sometimes during periods of rapid change, the places that structured people's lives were transformed beyond recognition. A river mouth became an estuary. An estuary became a bay. A village beside a freshwater marsh became a point beneath the tide. And eventually, the whole landscape lay offshore. If houses were made from wood and reeds, waves could tear them apart. If tools were scattered across the surface, currents could move them. If graves lay in sandy soil, erosion could erase them. If a settlement stood near an old river channel, later marine sediments might bury it under meters of mud. That is how a real human landscape can vanish without leaving a dramatic underwater skyline. And this is why claims about drowned cities require caution. There are famous sonar images that appear to show walls, roads, foundations, even grids of buildings beneath the sea. Some may eventually prove significant. Many do not. Nature creates straight lines. Sediment creates patterns. Rock fractures, reefs, tidal channels, and modern disturbances can look astonishingly artificial when viewed on a screen. Until archaeologists recover artifacts, establish dates, map the ancient land surface, and show that features belong together, a city is only a possibility. Sometimes not even that. The strongest conclusion is less sensational, but in some ways more profound. Landscapes vanished. Almost certainly. Settlements vanished with them. Camps, villages, gathering places, fishing grounds, ritual locations, and perhaps substantial coastal communities now lie beneath modern seas. But drowned cities, in the later historical sense of dense urban centres with monumental architecture, remain largely unverified for 10,300 BC. The mystery is real. It just may not look like Atlantis. It may look like ordinary human lives lived on shorelines that no longer exist. And if ordinary human lives were lived on shorelines that no longer exist, then another question becomes unavoidable. Could anyone have not remembered the exact date? Not remembered a sea level curve, a meltwater pulse, or a number like 10,300 BC? Nobody was writing down measurements of advancing shorelines. But could communities have remembered that the water used to be farther away? That there had once been hunting ground beyond the bay? That an island had been connected to the mainland? That ancestors had fled a drowning coast? Maybe. And this is where flood myths, oral traditions, and ancient stories enter the picture. Floods create powerful memories because floods are not abstract disasters. Fire destroys a home, drought empties a well, but a flood changes the map. It removes boundaries people thought were permanent. A river crosses its banks, and fields become lakes. A storm surge tears through a coastal village, and familiar landmarks disappear beneath brown water. A shoreline moves, and the place where your grandparents gathered shellfish is suddenly out beyond the tide. For communities living near coasts, rivers, lakes, and deltas, Water was always both life and danger. It brought fish, transport, fertile soil and trade. But it could also destroy everything with almost no warning. So it is not surprising that flood stories appear in cultures all over the world. The mistake is assuming that every one of those stories must be a literal report of the same geological event. They are not. A flood myth can preserve a memory of a real local disaster. It can also be a religious story, a moral warning, a political foundation myth, an explanation for why the world is imperfect, or all of those things at once. Stories change because people change them. They are told to children, adapted to new landscapes, connected to new beliefs, and reshaped by generations facing dangers their ancestors never saw. That does not make them meaningless. It makes them human. Consider the difference between a local flood memory and a universal deluge story. A local memory says, in effect, the sea took that land. There used to be dry ground where there is water now. Our ancestors travelled from that direction. A mountain, island, reef, or headland marks the boundary between the old world and the new one. A universal deluge story says something much larger. The entire world drowned, almost everyone died, and a small group survived to begin again. Those are not necessarily describing the same thing. For a small community living in a lowland basin, an enormous regional flood may have felt like the end of the whole world. Their world was the valley, the river, the coast, the neighbouring settlements, the hunting grounds they could reach in a few days. If all of it disappeared beneath water, they did not need a planet-wide catastrophe for the experience to feel universal. And over centuries, a local disaster can grow in the telling. A drowned village becomes a drowned valley. A drowned valley becomes a drowned kingdom. A storm that killed hundreds becomes a flood that destroyed everyone except the ancestors. This is not deception, it is how oral tradition works. Oral traditions are not frozen recordings. They are living systems for carrying knowledge across time. They can preserve details that matter for survival. Dangerous currents, seasonal storms, sacred springs, old travel routes, places where food can be found, and places people should not go. But they preserve those details through story, ritual, song, genealogy and metaphor, not through modern scientific language. In Australia, for example, some Aboriginal and Torres Strait Islander traditions describe coastlines changing, islands separating from the mainland, and lands now covered by the sea. Researchers have suggested that a few of these traditions may preserve distant memories of post-ice age sea level rise. That possibility is fascinating, but it has to be handled carefully. A tradition may be ancient without every detail remaining unchanged for thousands of years. It may contain environmental knowledge accumulated across many generations rather than a single eyewitness account. And outside researchers should not simply arrive, match a story to a sea level map, and announce that they have proved a myth. The communities who hold those traditions are not archives waiting to be decoded. They are living cultures with their own authority over what their stories mean. The same caution applies everywhere. Around the Mediterranean, Northern Europe, South Asia, the Pacific, the Americas and Africa, there are stories of drowned lands, angry seas, great floods, and ancestors escaping water. Some may reflect real experiences of coastal change. Some may refer to later river floods, tsunamis, storms, or lake outbursts. Some may have travelled between cultures and been retold in new forms. Mesopotamian flood stories, including versions found in the Epic of Gilgamesh, emerged from societies living between unpredictable rivers. The biblical flood story belongs to that wider ancient Near Eastern world. Greek traditions tell of Deucalion surviving a great deluge. Other cultures have their own stories of destruction and renewal through water. These narratives are important, but they do not provide evidence that one single flood covered the entire planet around 10,300 BC. Geology does not support that. What geology does show is something more complicated, and arguably more believable. As the Ice Age ended, many different landscapes were flooded at different times. Rivers surged, ice dams failed, coastlines retreated. Storms struck newly vulnerable shores. Entire lowlands slowly became seabed. For thousands of coastal communities, the water was not one event. It was a continuing pressure, a familiar world becoming smaller, wetter, saltier, and less predictable. And that kind of change is exactly the sort of thing people tell stories about. Not because stories are secret geological textbooks, but because when the land disappears, memory may be the only map that remains. But memory is not the only thing that remains. The sea floor remains too. Buried beneath sand, mud, peat, coral, and thousands of years of changing currents are the physical traces of the drowned world. And scientists have spent decades trying to read them. Drill cores, coral terraces, ancient shorelines, oxygen isotopes, ice sheet models, sediment layers from the bottom of the Atlantic. Every new piece of evidence brings the picture into sharper focus. And somehow, every new piece of evidence also creates a new argument. Because the basic story is not really in doubt. The Ice Age ended. Great ice sheets melted. Global sea level rose by more than 120 meters from its lowest point. Vast coastal plains disappeared. Human communities had to retreat, adapt, or abandon landscapes that had supported them for generations. But exactly how fast did the water rise around 10,300 BC? That is where the mystery stays open. Some researchers see evidence for abrupt meltwater pulses, periods when sea level rose dramatically faster than the long-term average, perhaps by several meters over a few centuries. Others think the evidence points to a more uneven but less catastrophic process, with rapid rises in some regions, pauses in others, and local events that can look global if you're only looking at one coastline. Even the names can be confusing. Scientists often refer to major episodes of accelerated sea level rise as Meltwater Pulse 1A, Meltwater Pulse 1B, and other proposed pulses. But these are not universally agreed upon disasters with exact beginning and ending dates stamped into the geological record. They are working labels for patterns seen in different datasets. Meltwater Pulse 1A, around 14,600 years ago, is widely recognized as a major rapid rise event. Estimates vary, but it may have raised global sea level by something like 12 to 20 meters in a few centuries. That is enormous. Not overnight, not in a single wall of water, but fast enough that shorelines could have retreated by kilometers within the lifespan of one family. The later period, closer to 10,300 BC, is more controversial. Some records suggest another significant acceleration, often associated with Meltwater Pulse 1B. Other researchers argue that the apparent pulse may actually be several smaller events spread across a longer period, and the timing itself shifts depending on how the record is dated. This matters more than it might seem. Move an event by a few centuries and it may line up with a different ice sheet collapse. Move it by 1,000 years and an entire explanation can fall apart. Was the water coming mainly from the collapsing Laurentide ice sheet over North America? Was it coming from Antarctica, from Eurasian ice sheets, from mountain glaciers melting across several continents at once? Or was it a combination with different ice sheets contributing at different times? Every answer has consequences. If the main source was North America, then scientists need to explain how meltwater escaped from ice-dammed lakes, crossed the continent and entered the oceans. If Antarctica was a major source, then the mechanisms become even more dramatic, Marine ice sheets destabilizing, ice shelves breaking apart, vast sectors of grounded ice retreating into deep basins below sea level. And the clues do not always agree. Corals are among the most important witnesses. Certain corals grow close to sea level, so fossil coral reefs can preserve a record of where the ocean surface once stood. Scientists can date them using uranium-thorium methods, which can be remarkably precise under the right conditions. A coral that grew in shallow water 12,000 years ago may tell us how high the sea was at that moment. But coral records are not perfect rulers. A reef can be lifted by tectonic forces. It can sink as the crust subsides. Storms can break it apart. Waves can move fragments from where they originally grew. And different coral sites record different parts of the planet's complicated response to melting ice. Then there is radiocarbon dating. For decades, radiocarbon dates have been essential for reconstructing ancient coastlines, drowned forests, peat beds, shell deposits, and human sites. But radiocarbon years are not identical to calendar years. The amount of carbon-14 in the atmosphere has changed through time. Ocean waters can make marine samples appear older than they really are, and calibration curves are constantly refined as new tree ring records, ice cores, lake sediments, and other datasets become available. That means an old date can change, not because somebody made it up, not because the science is failing, but because science is correcting itself as the measuring tools improve. A peat layer once assigned 1 century may be shifted earlier or later after recalibration. A sequence of sea level changes that seem to happen all at once may spread out across several centuries. Or a pattern that looked gradual may become sharper. This is why archaeologists and geologists can look at the same broad period and still disagree about the speed of change. And then there is the biggest complication of all. Global sea level is not the same thing as local sea level. Imagine an ice sheet thousands of kilometers away. Its enormous weight presses the Earth's crust downward. When that ice melts, the land beneath it slowly rebounds upward. In places once covered by ice, ancient shorelines can now sit high above the modern sea. But farther away, the opposite can happen. As ice melts, water redistributes across the oceans. The Earth's crust flexes. Sediments compact under the weight of rivers and deltas. Some coastlines sink, others rise. In a tectonically active region, an earthquake can lift or drop land by meters in a single event. So, when scientists find a drowned forest or submerged stone tools, they cannot immediately say global sea level rose this much. Maybe it did, but maybe the land sank, or maybe both happened at once. This is why the strongest reconstructions do not depend on one coral reef, one submerged village, or one dramatic sediment core. They compare records from many places. They test whether a proposed sea level jump appears in far separated regions. They model how each ice sheet would alter gravity, ocean circulation, and the shape of the Earth itself. They ask whether the source of the meltwater makes physical sense, because melting ice does not raise seas evenly. A massive ice sheet has gravity. It pulls ocean water toward itself. When the ice disappears, that gravitational pull weakens, and sea level can actually fall near the former ice sheet, even while it rises elsewhere. That sounds impossible at first, but it is one of the reasons ancient shorelines are so difficult to interpret. The models are not chosen because one makes the most dramatic story. They are tested. If a model says Antarctica supplied most of the water, does the Antarctic geological record show ice retreat at the right time? If it says North America released a huge flood, do lake sediments, river channels, and ocean chemistry show the expected signal? If a sea level curve predicts that Doggerland drowned rapidly in a particular window, do peat layers, Submerged river valleys and archaeological sites match that prediction. Sometimes they do, sometimes they do not. And when they do not, the model has to change. The discoveries that could transform this debate may already be waiting beneath shallow seas. Better sediment cores from drowned river valleys could preserve the exact sequence of flooding. More precisely dated corals from stable tectonic settings could narrow the timing of sea level jumps. High-resolution sonar could map ancient coastlines, lakes, marshes and settlement zones now hidden under the North Sea, the Persian Gulf, Sundaland and continental shelves around the world. And perhaps one day, archaeologists will find a submerged landscape with campsites, hearths, tools, food remains, and shorelines preserved together in a sequence that can be dated year by year. Then the question will no longer be only how fast the sea rose. It will be how people lived through it. And that brings us back to the people. Not the ice sheets, not the coral terraces, not the arguments over calibration curves and sediment layers. The people standing on a shoreline that would not stay still. Imagine living beside an estuary where your parents gathered shellfish, where your grandparents hunted along a river that crossed a wide coastal plain, where everyone knew the safe paths through the marsh. The land is familiar. Every hill has a name. Every bend in the river has a story. You know where the fish run in spring, where the deer move in autumn, where fresh water can still be found when the dry season comes. Then, slowly at first, that world begins to change. The highest tides reach farther inland. Salt water appears in places where grasses used to grow. The river becomes wider. Storm surges push over low ground that had never flooded before. A freshwater pond turns brackish. Trees near the shore begin to die. Nobody in that community needs a global sea level curve to understand what is happening. They can see it, and the most important thing is that this was not necessarily one single day of destruction. For many coastal communities after the Ice Age, the loss probably unfolded across lifetimes. A child might grow up playing on land that, by the time they were old, lay beneath the sea. A family could move its camp inland once, then again, then find that the inland route itself had become a coastline. That is still a catastrophe, not because a giant wave erased the world in one afternoon, but because the world you depended on kept disappearing, generation after generation. And in some places, change may have been much faster than the average. A rapidly rising sea, a collapsing coastal barrier, a severe storm, a river flood, or the sudden drainage of an ice-dammed lake could turn a long-term retreat into an immediate disaster. Lowlands do not need the ocean to rise by 10 meters in a week to become unlivable. Raise the water table, salinate the soil, flood the hunting grounds at high tide, cut off a familiar route, destroy a fish trap, a seasonal camp, or a freshwater source. A community can be forced to move long before its houses are actually underwater. This is what the drowned world means for us now. It is not a simple warning that the past is repeating itself exactly. It is not evidence that modern sea level rise will unfold in precisely the same way it did at the end of the Ice Age. The conditions are different. The ice sheets are different. The geography is different. The rate and causes of modern warming are different. Post-Ice Age people lived in small mobile communities with no cities, no ports, no electrical grids, no billion-dollar infrastructure concentrated along coasts. But the basic human problem is painfully familiar. Coasts are where people gather. They are rich places. Rivers meet seas, fish, shellfish, wetlands, fertile floodplains, sheltered harbours, trade routes and fresh water can all exist within a short distance of each other. That is why ancient people lived there. That is why modern people live there too. Today, hundreds of millions of people occupy low-lying coastal zones. Great cities sit on deltas, estuaries, barrier islands, and reclaimed land. Roads, railways, airports, factories, ports, farms, and homes are built in places where even a small shift in sea level can have enormous consequences. And unlike a small hunter-gatherer group, a modern coastal city cannot simply pick up and move inland. You cannot relocate a subway system in a season. You cannot move a port, a hospital network, a power grid, and millions of people without immense cost. You cannot easily replace a delta once salt water enters its soils and pushes upstream through rivers and groundwater. So the story of the drowned landscapes is not just about ancient loss. It is about adaptation. The people of the early Holocene were not helpless victims waiting for the sea to take them. They moved, they changed hunting grounds, they altered seasonal routes. They built new networks, they carried tools, knowledge, stories, and family ties into new territories. Some may have followed retreating coastlines. Others may have moved upriver or into higher country. Some communities probably merged with neighbours. Others may have fragmented, fought over resources, or disappeared from the archaeological record entirely. Human beings have always adapted, but adaptation is not the same thing as avoiding suffering. A family can survive and still lose its homeland. A culture can continue and still lose sacred places, burial grounds, food sources, and the landscapes that gave its stories meaning. The archaeological record often preserves stone tools better than grief. It can show us where people went. It is much harder to show us what they left behind. And that is why the phrase "cities vanished" needs to be handled carefully. What do we know? We know that global sea level rose by more than 120 metres after the last ice age. We know that enormous areas of continental shelf were once dry land. River valleys, marshes, plains, lakeshores and coastlines that are now submerged beneath the North Sea, the Persian Gulf, the Sunda Shelf and waters around every continent. We know people lived near coasts throughout this period. We know many coastal communities would have been displaced as the sea advanced. Those are not guesses. They are among the strongest conclusions in the entire story. What remains uncertain is more specific and more dramatic. Did a single, precisely dated meltwater pulse around 10,300 BC cause sea level to rise with exceptional speed worldwide? Maybe there's evidence for rapid rise during the broader deglacial period. But the exact timing, size, and global significance of the event near 10,300 BC remain debated. And did actual cities vanish beneath the waves? That depends on what we mean by cities. There is currently no solid evidence for lost Ice Age cities in the modern sense. Dense urban centres with monumental architecture, streets, palaces, and large permanent populations, all suddenly swallowed by a global flood around that date. That claim goes beyond the evidence. But settlements, camps, fishing villages, seasonal gathering places, sacred sites, early coastal communities with buildings made of wood, reeds, hides, and earth. Those are not only possible in many drowned landscapes, they are exactly what archaeologists expect to find. The problem is that the best places to look are now underwater. A campsite on an exposed Ice Age plain may lie beneath 30, 50 or 100 metres of water. It may be buried under sediment. Its wooden structures may have rotted away. Waves may have scattered its artefacts. Trawlers may have disturbed the seabed. Rivers may have cut through it before the sea arrived. And even if something survived, finding one small settlement across thousands of square kilometres of submerged landscape is like searching for a single fire pit in an entire country. Still, the seabed has surprises. Every submerged forest, every drowned peat bed, every ancient river channel, every stone tool recovered from a trawler's net is a reminder that the maps we know are temporary. The familiar coastline is not permanent. It is only the latest version of a boundary that has moved again and again throughout human history. Under the water are landscapes where people walked, hunted, loved, buried their dead, raised children and told stories beneath skies that looked almost exactly like ours. We have explored more of the moon than we have of some parts of our own continental shelves. And beneath those shallow seas may lie one of humanity's largest unexplored archives. Not a fantasy world, a real one. A world drowned not because it was imaginary, but because the planet changed, the ice melted, and the sea came in. If you enjoyed this journey into the drowned world, please like the video, subscribe, and let us know in the comments where you're listening from. And if you want to support the channel in the best possible way, listen on Spotify through the link in the description.